In the endless stretches of space where stars shine and galaxies drift, incredible mysteries await. From the wild storms on distant planets to the strange depths of black holes, the universe is full of secrets that defy our understanding. Join us on an exciting journey to uncover the most mind-blowing mysteries in our universe. The Great Red Spot on Jupiter, a massive storm larger than Earth, has baffled scientists since its discovery in the 17th century. One of the most mysterious features of this colossal tempest is its longevity. Despite the dynamic and chaotic nature of Jupiter's atmosphere, the Great Red Spot has persisted for over 300 years. Researchers initially thought such a storm would be short-lived due to turbulent winds surrounding it, yet it has remained a dominant feature on the planet. Scientists now suggest that the spot's impressive size and depth, extending possibly 100 miles into the planet's atmosphere, contribute to its prolonged existence by preventing smaller storms from dissipating its energy. Another enigma surrounding the Great Red Spot is its characteristic crimson hue. While the storm is visually striking, the precise reason for its red coloration remains elusive. Various hypotheses propose that the color could be due to complex chemical reactions involving the trace amounts of sulfur and phosphorus-containing compounds in Jupiter's atmosphere. These compounds might be altered by the sun's ultraviolet radiation, resulting in the ruddy appearance of the storm. Indeed, understanding the spot's coloration could offer insights into the chemical composition and environmental processes of Jupiter's upper atmosphere, a region still cloaked in mystery. Saturn's rings are one of the most captivating features in our solar system, spanning hundreds of thousands of miles yet astonishingly thin, no more than roughly 30 feet thick in some places. The primary factor that helps these rings maintain their structure is the gravitational influence of Saturn's numerous moons, often referred to as shepherd moons. These small moons exert gravitational forces that confine the ring particles, preventing them from dispersing into space. For instance, the moons Pan and Atlas play crucial roles in maintaining the integrity of the A ring and the thin F ring, respectively, by corralling the particles within defined boundaries. Additionally, the ring's stability is enhanced by the orbital resonance between certain moon and ring particle orbits. This phenomenon occurs when particles in the rings and the moons orbit at integer ratios, reinforcing gravitational interactions that help maintain the structure and organization of the rings. The result is a series of intricate and dynamic patterns that are continuously shaped and reshaped over time. Astronomers believe that the rings are composed primarily of water ice, mixed with dust and other chemical compounds, reflecting sunlight and creating their luminous appearance. Despite being an ancient structure, believed to be over 100 million years old, these rings are constantly evolving, offering a vivid lesson in celestial mechanics and the delicate balance maintained by gravitational forces in our solar system. The hexagonal storm on Saturn's North Pole is one of the most intriguing atmospheric phenomena observed in our solar system. Initially discovered by the Voyager spacecraft in the early 1980s, this geometric weather pattern is a vast, persistent cloud pattern in the shape of a hexagon, with each side exceeding the diameter of Earth. Scientists attribute the formation of this hexagon to a combination of atmospheric dynamics and fluid mechanics. Essentially, the hexagon is a standing wave pattern in Saturn's atmosphere, caused by the interaction between jets of air moving at different speeds. These atmospheric jets encircle the pole and are shaped by the planet's rapid rotation, which completes a full turn on its axis in just about 10 Earth hours. Laboratory experiments and computer simulations have further elucidated how such a shape could naturally occur. When fluids at different rotational speeds create shear regions, polygonal patterns can emerge. In Saturn's case, the differential rotation speeds in its atmosphere create a stable wave that takes on a hexagonal form. Moreover, the hexagon's stability and persistence suggest it is deeply embedded in Saturn's atmospheric layers, influenced by deeper rotational currents. Another layer of complexity is added by the shifting colors observed within the hexagon over time, driven by seasonal changes that affect the planet's chemical composition and sunlight exposure. Understanding this hexagonal storm not only provides insight into Saturn's meteorological mechanisms, but also offers broader implications for the study of fluid dynamics and atmospheric sciences. Uranus's peculiar rotation, almost sideways compared to the orbital plane of the solar system, is one of its most mysterious and distinctive features. This extreme axial tilt, about 98 degrees, means that Uranus essentially rolls around the Sun on its side, leading to extreme seasonal variations. Scientists believe this unique orientation was likely caused by one or more colossal collisions during the planet's formative years over 4 billion years ago. A massive impact with a protoplanetary body, possibly as large as Earth, could have knocked Uranus into its sideward tilt, forever altering its rotation. Further supporting this collision theory is Uranus's internal heat distribution and magnetic field, which are both highly irregular compared to other planets. The giant impact hypothesis posits that the force of the collision would not only tilt Uranus, but also disrupt its internal structure, affecting its heat distribution from the core to the surface. This disruption might explain why Uranus radiates relatively little heat compared to its fellow gas giants. Additionally, the planet's magnetic field is tilted approximately 60 degrees from its rotational axis and offset from the planet's center, suggesting that its internal dynamics are quite unusual. This asymmetric magnetic field could also result from the turbulent aftermath of the proposed ancient collision, making Uranus a captivating subject for further astronomical study. Neptune's dark spots, first observed by the Voyager 2 spacecraft in 1989, are enigmatic and dynamic storms that fascinate astronomers. Unlike the Great Red Spot on Jupiter, these storms are temporary, appearing and disappearing over several years. The leading theories behind their formation revolve around the planet's atmospheric dynamics and unique composition. Primarily, these dark spots are thought to be high-pressure systems, akin to anticyclones on Earth, formed much higher in Neptune's atmosphere. They appear as dark spots because they lack the translucent, ammonia-rich clouds that permeate other parts of the planet, revealing deeper layers composed of methane and hydrogen sulfide. The stability and movement of these dark spots are attributed to Neptune's differential rotation and intense wind speeds, which can exceed 1,200 miles per hour. These rapid winds and the planet's internal heat create turbulence in the atmosphere, likely fostering conditions conducive to the formation of dark spots. Furthermore, the extreme cold in Neptune's upper atmosphere, around -373 degrees Fahrenheit, contributes to the peculiar chemistry and cloud dynamics, allowing these storms to manifest with their distinct dark appearance. The temporary nature of the dark spots, in contrast to Jupiter's persistent Great Red Spot, suggests that Neptune's atmospheric conditions are highly volatile and undergo significant changes over relatively short timescales, providing an area ripe for ongoing investigation and discovery in planetary science. The asteroid belt, a vast region populated by rocky remnants, lies between the orbits of Mars and Jupiter. Its formation is closely tied to the early dynamics of our solar system, dating back about 4.5 billion years. The prevailing theory suggests that the asteroid belt is comprised of primordial materials that never coalesced into a planet. In the nascent solar system, planetesimals, the building blocks of planets, collided and merged to form the planets we know today. However, in the region of the asteroid belt, Jupiter's immense gravitational influence disrupted this process. The gas giant's powerful gravity stirred up the region, causing collisions to be too violent for accretion into a larger planetary body, resulting instead in a collection of countless smaller fragments. These remnants hold profound secrets about the early solar system's conditions and composition. By studying the asteroids, scientists can glean insights into the primordial material from which the planets formed, offering a window into the processes of planetary formation and differentiation. Certain asteroids are composed of relatively unaltered material, preserving the original chemical signatures from the solar system's birth. These ancient rocks can reveal information about the distribution of water and organic compounds, shedding light on the origins of water and possibly life on Earth. Furthermore, missions like NASA's OSIRIS-REx to Bennu and Japan's Hayabusa 2 to Ryugu aim to return samples from these bodies, promising to unlock more secrets bound within their ancient surfaces. Venus, often referred to as Earth's twin due to its similar size and composition, presents a stark contrast to our own planet, with its hellish environment of scorching temperatures and crushing atmospheric pressure. The transformation of Venus from a potentially habitable world to its current inhospitable state is attributed to a runaway greenhouse effect. Billions of years ago, Venus may have had liquid water and conditions conducive to life. However, intense volcanic activity released vast quantities of carbon dioxide into the atmosphere. Without a robust mechanism to sequester this carbon, like Earth's carbon cycle involving rock weathering and biological processes, the greenhouse gases accumulated unchecked. The thickening carbon dioxide atmosphere trapped increasing amounts of solar heat, leading to skyrocketing temperatures. As the temperatures rose, any existing oceans started to evaporate, adding water vapor, a potent greenhouse gas, into the atmosphere, further amplifying the heating in a vicious cycle. This runaway greenhouse effect led Venus to reach surface temperatures exceeding 800 degrees Fahrenheit, hot enough to melt lead, and pressures over 90 times that of Earth's at sea level. Additionally, the lack of a significant magnetic field allowed the solar wind to strip away lighter elements from the atmosphere, including hydrogen from any water vapor, making the loss of water irreversible. The dramatic transformation of Venus serves as a cautionary tale about the impact of greenhouse gases on planetary climates. Understanding Venus's past and its climatic evolution provides critical insights into atmospheric dynamics and offers valuable lessons for comprehending Earth's climate system and the potential future impacts of anthropogenic climate change. Olympus Mons on Mars stands as the tallest volcano and one of the most striking features in our solar system, rising around 13 miles above the Martian surface, more than twice the height of Mount Everest. Its immense size can be primarily attributed to Mars's lower gravity, which is about 38% that of Earth. This reduced gravitational force allows Martian volcanoes to grow taller before their structure collapses under their own weight. Additionally, the lack of plate tectonics on Mars plays a crucial role. Unlike Earth, where tectonic plates shift and new volcanic structures form over them, Martian volcanoes remain stationary over their magma sources. This allows them to undergo prolonged eruptions and continuous lava flow, accumulating vast amounts of material in one location over millions of years. Despite its prominence, Olympus Mons holds several mysteries that continue to intrigue scientists. One of these is the volcano's relatively young age in geological terms, with estimates suggesting its last eruption occurred around 25 million years ago, a mere blink in the planet's history. This raises questions about the current state of volcanic activity on Mars and whether the planet could still harbor some geothermal activity beneath its surface. Another enigma is the existence of the caldera complex at its summit, which consists of multiple overlapping collapse craters, indicating a series of eruptive phases. Understanding the exact sequence and scale of these eruptions could provide deeper insights into the planet's geological and volcanic history. Furthermore, the sheer size and structure of Olympus Mons, with its broad shield-like shape and immense lava flows, suggest that the volcano's formation involved not only typical basaltic eruptions, but potentially unique volcanic processes not fully understood. The study of Olympus Mons thus offers a significant opportunity to learn about comparative planetology, volcanic activity on other planets, and the evolutionary trajectories of volcanic features in varying planetary environments. The Kuiper Belt, a vast region beyond Neptune's orbit teeming with icy bodies and dwarf planets like Pluto, is a relic from the early solar system and provides crucial insights into its formation and evolution. These Kuiper Belt objects, KBOs, are thought to be remnants of the primordial solar nebula that never coalesced into full-fledged planets. During the solar system's nascent stages, the outer regions contained a vast disk of gas and dust that gradually clumped together into larger bodies through a process called accretion. However, the region's low density and the presence of massive planets like Neptune disrupted the aggregation process, leaving behind a swarm of smaller icy objects. Over billions of years, gravitational interactions, especially with Neptune, have significantly shaped the Kuiper Belt's structure. For example, many KBOs, including Pluto, are in a special orbital resonance with Neptune. Pluto follows a 2-to-3 resonance, meaning it orbits the Sun twice for every 3 Neptune orbits. This gravitational dance ensures their paths do not intersect, stabilizing their orbits. Such resonant interactions have sculpted the Kuiper Belt into a complex and dynamic region, segregating objects into different populations based on their orbital characteristics. The evolution of KBOs like Pluto involves not just their orbital dynamics, but also their internal and surface changes. Pluto's surface, for instance, exhibits a variety of terrains, suggesting a history of geological activity. The New Horizons mission in 2015 revealed that Pluto has mountains, plains, and even evidence of possible cryovolcanism, volcanoes that erupt with water, ammonia, or methane instead of molten rock. These features indicate that despite their distance from the Sun, the KBOs could experience internal heating driven by radioactive decay or tidal interactions, which might cause these icy worlds to remain geologically active over immense timescales. Understanding how Kuiper belt objects formed and evolved sheds light on the conditions and processes that occurred in the outer solar system. Studying these distant icy bodies helps scientists piece together the broader narrative of planetary formation and migration, providing a fuller picture of our cosmic neighborhood's intricate history. Mercury, the smallest and innermost planet in our solar system, presents a variety of enigmatic features that continue to intrigue scientists. One of the most puzzling anomalies observed on Mercury's surface is the presence of hollows. These are shallow, irregular depressions with bright reflective halos that differentiate them from typical impact craters. The formation mechanisms behind these hollows remain unclear, but they are hypothesized to result from the sublimation or direct transition from solid to gas of volatile elements. Such volatiles might have been brought to the surface by volcanic activity or outgassing from the planet's interior, resulting in the creation of these mysterious, ever-changing depressions as they evaporate under the Sun's intense heat. Another anomaly on Mercury's surface is the existence of unusual, large and unexplainable scarps or cliffs known as lobate scarps. These are believed to be thrust faults, formed as Mercury's core cooled and contracted over billions of years. However, what perplexes scientists is the recent evidence suggesting that some of these tectonic features may still be geologically active. Data from NASA's Messenger mission indicated that these scarps might have experienced seismic activity in relatively recent geological timescales, which challenges our understanding of Mercury's thermal evolution and raises questions about the planet's current internal dynamism. Additionally, Mercury's extreme temperature fluctuations, which range from 800 degrees Fahrenheit during the day to minus 290 degrees Fahrenheit at night, contribute to surface anomalies. For instance, the planet's surface is dotted with secondary craters and ejecta patterns that seem more chaotic than those on other solar system bodies. This could be due to the interaction between Mercury's regolith and its tenuous exosphere, influenced by solar radiation and micrometeorite impacts. These anomalies on Mercury's surface not only add layers of mystery to the planet, but also hold keys to deciphering the broader processes of planetary formation and evolution. As scientists continue to study Mercury through missions like BepiColombo, our understanding of these surface features will likely expand, offering deeper insights into the dynamic history of the smallest rocky planet in our solar system. Detecting exoplanets, which are planets orbiting stars beyond our solar system, is a challenging endeavor given their vast distances and faint visibility compared to their host stars. However, scientists have developed several ingenious methods to discover and study these distant worlds. One of the most successful techniques is the *** transit method ***, which involves observing the periodic dimming of a star's light caused by an exoplanet passing in front of it. These tiny decreases in brightness, though often less than 1%, can be detected by space telescopes like NASA's Kepler and TESS, Transiting Exoplanet Survey satellite. By analyzing these transit events, astronomers can deduce the exoplanet's size, orbital period, and even some atmospheric properties if the planet's atmosphere filters starlight. Another prevalent method is the *** radial velocity or Doppler technique ***, which measures changes in a star's spectrum of light caused by the gravitational pull of an orbiting planet. As the planet orbits, it induces a small wobble in the star's motion, shifting its light spectrum toward the red end when moving away and toward the blue end when moving closer. High-precision spectrometers can detect these minute shifts, allowing scientists to infer the presence of an exoplanet and estimate its mass and orbit. Ground-based observatories equipped with sensitive instruments like the HARPS, High-Accuracy Radial Velocity Planet Searcher, have been particularly effective in utilizing this method. Another fascinating technique is *** direct imaging ***, which involves capturing pictures of exoplanets directly by blocking the light of the host star. This method is more suited for young, massive exoplanets located far from their stars, often employing specialized instruments and techniques like coronagraphs or starshades to suppress the starlight. While challenging due to the planet's faintness and proximity to their bright parent stars, advancements in adaptive optics and next-generation telescopes like the James Webb Space Telescope aim to enhance the feasibility of this method. There's also the *** gravitational microlensing *** method, which takes advantage of the gravitational field of a star and its planet to bend and magnify the light of a more distant background star. When such an alignment occurs, the resulting light curve can reveal the presence of the planet. This technique is particularly useful for detecting planets that orbit far from their host stars or are not easily detectable by other methods. Each detection technique has its strengths and limitations, often providing complementary information that, when combined, offers a richer understanding of these distant worlds. As technology and observational methods continue to advance, the discovery and study of exoplanets will only become more precise, expanding our knowledge of the universe beyond our solar system. Hot Jupiters are a class of exoplanets that are physically similar to Jupiter in terms of their massive size and gaseous composition, but orbit extremely close to their host stars, often closer than Mercury is to the Sun. These exoplanets can have orbital periods as short as a few days, resulting from their close proximity to their star. This proximity causes them to be intensely heated, with temperatures soaring to several thousand degrees Fahrenheit. The intense radiation from the parent star can cause the atmospheric composition of these planets to differ significantly from cooler gas giants, leading to phenomena such as strong winds, significant atmospheric expansion, and potential mass loss by atmospheric evaporation. The exact mechanisms behind the formation and migration of hot Jupiters are still subjects of ongoing research and debate. One leading hypothesis suggests that these giant planets initially form in the cooler outer regions of their star's protoplanetary disk, much like Jupiter in our own solar system. Over time, gravitational interactions with the disk or other giant planets lead them to migrate inwards. These interactions can be explained by different mechanisms, such as disk-driven migration, where interactions between the planet and the gas of the protoplanetary disk create waves that transfer angular momentum and cause the planet to spiral inward. Another possible explanation involves dynamic interactions with other planets or stellar companions. In such scenarios, gravitational perturbations from these bodies could send a giant planet into an elongated elliptical orbit that gradually circularizes and tightens due to tidal forces, ultimately resulting in a close, stable orbit, the hallmark of a hot Jupiter. The presence of hot Jupiters so close to their stars challenges traditional models of planetary system evolution, offering valuable insights into the dynamism and diversity of planetary systems beyond our own. These extreme worlds also serve as natural laboratories for studying atmospheric physics under intense irradiation, contributing to our broader understanding of exoplanetary atmospheres and the myriad ways planet-star interactions can shape planetary systems. The discovery of potentially habitable exoplanets, worlds that might harbor conditions conducive to life, remains one of the most intriguing and challenging frontiers in modern astronomy. One major mystery revolves around the precise definition of habitability. Traditionally, scientists have focused on the habitable zone or Goldilocks zone around a star where conditions are just right for liquid water to exist on a planet's surface. However, recent discoveries suggest that other factors, such as the planet's atmosphere, geological activity, and magnetic field, play significant roles in sustaining life. For instance, the detection of exoplanets around red dwarf stars, like the 7 Earth-sized planets in the TRAPPIST-1 system, raises questions about the potential for habitability around such stars, given their propensity for stellar flares and varying luminosity. Another mystery is the complex nature of these exoplanets' atmospheres and compositions. While the transit method can reveal a lot about a planet's size and orbit, and the radial velocity method can provide its mass, understanding the atmosphere's composition is far more challenging. Recent advances in spectroscopy have allowed astronomers to analyze the light filtered through an exoplanet's atmosphere during a transit event, revealing the presence of compounds like water vapor, methane, and oxygen. However, interpreting these data is fraught with ambiguity. For example, while the presence of oxygen might suggest biological processes, it could also result from non-biological processes such as photodissociation of water molecules. The discovery of potentially habitable exoplanets also poses the enigma of their true climatic and geophysical states. The detection of exoplanets with Earth-like dimensions does not automatically mean they have Earth-like conditions. For instance, the planet's rotation and tilt, ocean currents, and volcanic activity can drastically affect its climate and potential to support life. Instruments like the James Webb Space Telescope aim to offer more detailed analyses of exoplanetary atmospheres, but for now, many questions remain about these distant worlds' true nature. Finally, the mystery extends to the potential for life itself. What if life on other planets does not conform to the biochemistry we know on Earth? The search for biosignatures, indicators of life, might need to be broader than looking for Earth-like conditions and chemistry. The discovery of extremophiles on Earth, organisms that thrive in conditions previously deemed uninhabitable, has broadened our perspective on where life might exist. Hence, scientists are also considering habitability beyond the traditional scope, including subsurface oceans on moons like Europa and Enceladus, which might be mirrored on exoplanets. Each discovery of a potentially habitable exoplanet brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? Yet each discovery also underscores the complexity and diversity of planetary systems, continually expanding our understanding of what it means for a world to be truly habitable. Super-Earths are a fascinating class of exoplanets that are more massive than Earth, but significantly less massive than the ice giants, Neptune and Uranus. Typically, their masses range from about 1 to 10 Earth masses. Despite the name, super-Earths are not necessarily similar to Earth in terms of composition or habitability. They offer a diverse range of characteristics that can differ significantly from our own planet. One of the primary ways super-Earths differ from Earth is in their size and mass, which have significant implications for their structure and geology. A higher mass generally leads to stronger gravitational forces, which in turn affects the planet's atmosphere. Super-Earths might have denser, thicker atmospheres, potentially dominated by gases like hydrogen and helium, particularly if they formed in the outer regions of their star's protoplanetary disk and migrated inward. These thick atmospheres could lead to higher surface pressures and temperatures, making conditions very different from those on Earth. The interior composition of super-Earths can also vary widely. Some might be rocky worlds with large iron cores, while others could be water-rich, resembling scaled-up versions of Earth's oceans. The presence of large quantities of water could lead to extensive global oceans, possibly hundreds of miles deep, creating what are known as water worlds. In such environments, the oceanic pressure at the bottom would be immense, potentially affecting the geochemical cycles and any potential life forms. Another intriguing aspect of super-Earths is their potential for tectonic activity. Larger planets might retain internal heat for longer periods, supporting vigorous plate tectonics, which could be crucial for maintaining a stable climate and recycling essential minerals and gases. However, the exact nature of tectonic processes on super-Earths remains speculative, given that we currently understand tectonics only in the context of Earth. Furthermore, the climate and weather systems on super-Earths could be radically different. Thick atmospheres and strong greenhouse effects might maintain high surface temperatures, while rapid rotation could lead to intense weather patterns and storm systems. Conversely, some super-Earths may have atmospheres with compositions that allow for more temperate climates, potentially creating habitable conditions. Given their diversity, super-Earths represent a broad class of planets that challenge our understanding of planetary formation and habitability. They might range from hostile, high-pressure worlds with crushing atmospheres to temperate, ocean-covered planets with conditions potentially suitable for life. The study of super-Earths is still in its infancy, but with advancements in telescopes and observational techniques, the mysteries of these intriguing planets will likely continue to unfold, deepening our understanding of the myriad ways planets can form and evolve. When scientists began detailed investigations of exoplanet atmospheres, they encountered a series of astonishing discoveries that extended our understanding of planetary science. One of the most unusual features detected was the presence of elements and compounds not commonly found in such forms within our solar system. For instance, on the exoplanet HD 189733b, researchers discovered traces of silicate particles within the upper atmosphere. These silicates likely form rain made of molten glass, which falls sideways due to the planet's extreme wind velocities of up to several kilometers per second. This intriguing atmospheric phenomenon creates a vision of a celestial object quite foreign to Earth's more placid weather systems. Equally fascinating are the photochemical processes occurring in the atmospheres of gas giants that orbit very close to their host stars, known as hot Jupiters. The intense heat from the nearby stars causes a separation of molecular hydrogen into atomic hydrogen, and ultraviolet light from the star can energize these atoms to create a glowing, escaping cloud of hydrogen gas. This was directly observed in the exoplanet HD 209458b, where astronomers noted a comet-like tail composed of hydrogen trailing behind the exoplanet. It points to dynamic atmospheric escape processes that can significantly alter a planet's complexion over astronomical timescales, reshaping our understanding of atmospheric evolution and planetary life cycles. Rogue planets, also known as interstellar planets or orphan planets, are celestial bodies that wander through the vast expanse of space without the gravitational anchor of a parent star. Unlike planets within a solar system that have stable elliptical orbits around a star, rogue planets drift through the galaxy, moving in trajectories set by their often tumultuous past. These solitary travelers are thought to have been ejected from young planetary systems due to gravitational interactions, which may involve close encounters with other massive planets or passing stars. As developing planetary systems undergo chaotic phases, gravitational forces can impart significant velocities to planets, flinging them into interstellar space. The journey of a rogue planet is in many ways a solitary and cold expedition. Without the warmth of a nearby star, these planets rely solely on residual heat from their formation and potentially internal radioactive decay to maintain any semblance of warmth. Surprisingly, it's hypothesized that some rogue planets could harbor subsurface oceans kept liquid by geothermal energy, despite their frigid outer environs. These planets continue their silent voyage, traversing the Milky Way at speeds often reaching tens of kilometers per second. Their paths are influenced only by the gravitational pull of the galaxy and any stars they might pass close to, occasionally altering their trajectory, but never providing the stable orbit they once knew. Studying exoplanetary weather systems presents a myriad of profound challenges, primarily due to the vast distances between us and these distant worlds. Unlike weather observations on Earth, which can be conducted using a plethora of complex instruments and satellites providing high-resolution data, astronomers must rely on indirect methods, such as spectroscopy when examining exoplanets. Spectroscopic observations require incredibly precise measurements of light emanating from or passing through a planet's atmosphere. This task is particularly daunting because the light from the exoplanet is often faint and easily drowned out by the overwhelmingly bright light of its host star. Distinguishing between the two typically involves complex data processing and advanced telescopes equipped with sophisticated instruments, including space-based observatories like the Hubble and James Webb Space Telescopes. Moreover, the dynamic nature of weather systems adds another layer of complexity to these studies. Weather on exoplanets, especially those with extreme environments such as hot Jupiters, can change rapidly and is driven by factors far more diverse than what we're accustomed to on Earth. These include intense stellar radiation, high-speed winds, and unusual atmospheric compositions. Differential heating on the day side and night side of tidally locked planets, which never rotate to show their night side to the star, can lead to fierce storms and broad-scale atmospheric circulation patterns that are incredibly difficult to model with our current understanding. In addition, the limited observational time available on powerful telescopes and the occasional interference from our own atmospheric conditions further hinder the ability to create accurate, long-term weather models for exoplanets. These considerable challenges make the study of exoplanetary weather a frontier filled with both obstacles and exciting potential discoveries. The formation of exoplanets in binary star systems complicates an already intricate process, presenting scenarios where gravitational forces interplay in fascinating and often chaotic ways. In a binary system, where two stars orbit a common center of mass, the gravitational influence of each star can shape the protoplanetary disk, a rotating disk of gas and dust from which planets coalesce, in unique ways. Generally, two primary scenarios dictate how planets might form in these environments: the circumbinary and circumstellar configurations. In a circumbinary setup, planets form in a disk that encircles both stars. Here, the combined gravitational pull of the binary stars influences the protoplanetary material, potentially stabilizing or destabilizing certain regions of the disk. However, the inner parts of the circumbinary disk are usually void of solid material due to dynamic perturbations, pushing the planet formation regions further out. Despite these challenges, discoveries of planets like Kepler-16b, a circumbinary planet, prove that planet formation can and does occur in such conditions, albeit with unique orbital characteristics influenced by the dual star dynamics. Conversely, in a circumstellar scenario, planets form around just one of the stars in the binary pair. The gravitational forces from the companion star can induce eccentricities in the protoplanetary disk, leading to variations in the disk's density and temperature. These variations can either hinder or foster planet formation, depending on how pronounced these gravitational perturbations are. Important factors include the distance between the two stars and the mass ratio of the binary system. Planets in these configurations often have more eccentric orbits compared to those in single-star systems due to ongoing perturbations by the secondary star. This distinctive environment prompts planets to follow unique developmental pathways, showcasing the diverse possibilities of planetary formation in our universe. When scientists search for potential signs of life on exoplanets, they focus on a broad spectrum of biosignatures, indicators that could imply the presence of biological activity. One of the primary biosignatures is the detection of certain gases in a planet's atmosphere, particularly those that are often associated with life as we know it. Oxygen, for instance, is a key indicator because it is continually replenished by biological processes such as photosynthesis on Earth. In the absence of ongoing biological activity, free oxygen would typically react with other elements and not remain in a planet's atmosphere in significant amounts. Similarly, methane is another compelling biosignature, especially when found alongside oxygen, as it would likely need a constant source to maintain equilibrium given its relatively short lifespan in atmospheric conditions. Beyond individual gases, scientists look at the overall atmospheric composition and the potential for complex interactions that could suggest life. For example, the simultaneous presence of gases like ozone and nitrous oxide, or a specific ratio of carbon dioxide and water vapor, might suggest biological processes. In addition to gaseous components, the detection of organic molecules, complex carbon-based compounds that are fundamental to life, can also be a significant indicator. Instruments like those on the James Webb Space Telescope are designed to identify such molecules through detailed spectroscopic analyses of starlight filtered through an exoplanet's atmosphere. Moreover, scientists also observe planetary surface conditions and potential habitability factors. Signs of liquid water, either on or beneath the surface, are considered quintessential markers of life-supporting conditions, as water is a solvent for many biochemical reactions. The planet's position within the habitable zone of its star, where temperatures are conducive to the presence of liquid water, also plays a crucial role. The search for life involves a holistic approach that combines these potential biosignatures, the atmospheric and surface conditions, and understanding the planet's environmental stability over time, giving scientists the tools to make educated guesses about the likelihood of life beyond Earth. Exoplanetary moons, often referred to as exomoons, could significantly contribute to the habitability of the host exoplanets, or even be potential sites of habitability themselves. These moons can play several roles in creating and maintaining environments where life might flourish. One of the primary mechanisms is through tidal heating, which can provide a substantial and consistent source of internal heat, particularly for moons orbiting large gas giants. Tidal heating occurs due to the gravitational pull between the Moon and its planet, causing flexing and frictional heating within the Moon's interior. This process can maintain subsurface oceans in a liquid state, as is theorized for moons like Europa and Enceladus in our own solar system, thereby offering potential niches for life. Additionally, an exomoon's orbit can influence the axial tilt of its host planet, which in turn can stabilize the planet's climatic conditions. A stable axial tilt ensures more regular seasonal variations, which could foster an environment conducive to complex life by preventing extreme climatic swings. Moons can also aid in bolstering the protection of the host planet's atmosphere from solar wind stripping, particularly if the Moon itself possesses a magnetic field. This magnetic shield can create a more stable atmosphere, essential for sustaining liquid water and, consequently, life. Furthermore, exomoons might themselves harbor conditions favorable to life, independent of their host planets. If such moons exist within the habitable zone of their star system, they could potentially have atmospheres, liquid water, and other life-supporting characteristics. Observations with current and upcoming astronomical instruments aim to measure and analyze the atmospheres and compositions of these moons, searching for signs of geological activity, water vapor, and even biosignatures, similar to those sought after on exoplanets. The presence of exomoons adds additional layers of complexity and opportunity to the search for habitable environments beyond our solar system. Their contributions to tidal heating, climatic stability, and atmospheric protection all enhance the potential for life-supporting conditions on both the exomoons and their host exoplanets, making them exciting targets for future exploration and study. Black holes, some of the most enigmatic objects in the universe, come in various types, differing primarily in size and mass. These cosmic entities can be broadly classified into three main categories: stellar mass black holes, supermassive black holes, and intermediate mass black holes, each with distinct formation processes and characteristics. Stellar mass black holes are the most common type and form from the remnants of massive stars. When a star with a mass greater than approximately 25 times that of our Sun exhausts its nuclear fuel, it undergoes a supernova explosion. The core that remains can collapse under its own gravity to a point of infinite density, known as a singularity, enveloped by an event horizon beyond which nothing can escape. These black holes typically range from a few to several tens of solar masses and are scattered throughout galaxies, including our Milky Way. Supermassive black holes residing at the centers of most galaxies are a different beast altogether, boasting masses ranging from hundreds of thousands to billions of solar masses. Their formation is a subject of ongoing research and debate, but several theories exist. One hypothesis suggests they form from the merging of many smaller black holes and massive stars in the dense central regions of young galaxies. Another theory posits that they could have originated from the direct collapse of massive gas clouds in the early universe. Over time, these enigmatic giants grow by accreting matter from their surroundings and merging with other black holes, thus becoming the colossal structures that anchor galaxies. Intermediate mass black holes, occupying the size range between stellar mass and supermassive black holes, remain somewhat elusive and less well understood. These black holes are thought to form through the merging of stellar mass black holes in dense star clusters, or via the direct collapse of very massive stars in low metallicity environments. They range from hundreds to thousands of solar masses and might represent an evolutionary bridge between stellar mass and supermassive black holes. Although few confirmed examples of intermediate mass black holes exist, they offer critical clues about the scaling and growth processes that lead to supermassive black holes. Each type of black hole provides a unique window into the universe's fundamental processes, offering insights into stellar evolution, galaxy formation, and the mysterious nature of gravity itself. Their formation mechanisms, albeit varied and complex, underscore the dynamic and ever-changing cosmos that continues to captivate scientists and enthusiasts alike. Black holes warp space-time through the profound effects of their immense gravitational fields, a concept that stems from Albert Einstein's general theory of relativity. This theory, formulated in the early 20th century, revolutionized our understanding of gravity, revealing that massive objects cause a curvature in the fabric of spacetime itself. A black hole, with its intense gravitational pull, represents one of the most extreme examples of this phenomenon. Imagine spacetime as a two-dimensional rubber sheet. When you place a massive object like a star on this sheet, it creates a depression or a dip, bending the sheet around it. A black hole, however, acts like placing an enormously heavy and compact object on the sheet, creating a well so deep and steep that it forms a kind of funnel. The closer you get to the black hole, the steeper the curvature becomes, culminating in a singularity at its center, where the curvature of spacetime becomes infinite. This warping has several observable effects. For one, light traveling near the black hole takes a curved path due to the highly curved spacetime. This phenomenon, known as gravitational lensing, can bend, distort, or even multiply the images of background stars or galaxies, creating spectacular astronomical observations. In the vicinity of the event horizon, the boundary beyond which nothing can escape the black hole's pull, time itself appears to slow down when observed from a distance, a consequence of the intense gravitational field. This effect, predicted by Einstein, is known as time dilation and has been confirmed through various experiments and observations. Moreover, the escape velocity within the event horizon exceeds the speed of light, rendering regular matter and signals unable to escape once they cross this threshold. Additionally, black holes can dramatically influence their surroundings through the accretion of matter. As matter spirals into a black hole, it forms an accretion disk, heating up to extreme temperatures and emitting X-rays and other forms of radiation. This process further underscores the black hole's ability to warp spacetime and energy around it. The warping of spacetime by black holes offers profound insights into the nature of gravity and the underlying structure of the universe. These intriguing objects continue to be the focus of intense scientific study, pushing the boundaries of our understanding and unveiling new mysteries of the cosmos. The event horizon of a black hole stands as one of the most enigmatic boundaries in the universe, enveloped in various mysteries that challenge our understanding of physics. As the defining edge of a black hole, the event horizon is the point beyond which nothing, not even light, can escape the gravitational pull of the singularity at the center. This boundary marks a region where our conventional understanding of space and time begins to break down. One of the most profound mysteries surrounding the event horizon is what happens to the information about matter that falls into a black hole. This conundrum, known as the information paradox, arises from the apparent contradiction between general relativity and quantum mechanics. According to general relativity, any information about the matter that crosses the event horizon is ultimately lost to the singularity, where it is thought to be compressed into an infinitely small point. However, quantum mechanics, which governs the microcosmic world, dictates that information must be conserved. The clash between these two foundational principles of physics has led to various theories and debates, most notably involving Stephen Hawking's proposal of Hawking radiation. Hawking suggested that black holes could emit radiation due to quantum effects near the event horizon, gradually evaporating over time and potentially allowing information to be released back into the universe in some scrambled form. This idea has spurred countless discussions and remains an active area of research. Another significant mystery revolves around the exact nature of the singularity that lies within the event horizon. The singularity is a point where gravitational forces become infinite and spacetime curvature reaches an extreme. Our current laws of physics, particularly general relativity, cannot adequately describe conditions at the singularity. This has led scientists to explore theories of quantum gravity, such as string theory and loop quantum gravity, in the hope of developing a unified framework that can reconcile the discrepancies between quantum mechanics and general relativity. These efforts aim to unveil the true nature of black holes' cause and the ultimate fate of the matter and energy trapped within. The event horizon also raises questions about the observable effects experienced by an object approaching it. From the perspective of a distant observer, an object falling into a black hole appears to slow down and become increasingly redshifted as it approaches the event horizon due to extreme gravitational time dilation. However, from the viewpoint of the object itself, it would cross the event horizon without experiencing any dramatic changes, heading towards the singularity. This paradox of perspectives underscores the complex and counterintuitive nature of relativity in the realm of intense gravitational fields. The event horizon of a black hole serves as a frontier where our understanding of the universe is put to the test, posing deep and tantalizing mysteries about the fundamental nature of matter, energy, space, and time. These unresolved questions continue to inspire theoretical and observational endeavors, driving the quest for new physics that can illuminate the darkest corners of our cosmos. Inside a black hole, current theories suggest a realm of extremes where our conventional understanding of physics bends and possibly breaks. The journey toward comprehending what happens within a black hole begins at the event horizon, the boundary beyond which nothing can escape. Once an object crosses this threshold, it is inescapably drawn toward the core of the black hole, experiencing conditions unlike any in the observable universe. As one falls into a black hole, the experience would drastically differ depending on the black hole's size. For a stellar mass black hole, the gravitational forces at the event horizon are immensely strong, causing a phenomenon known as spaghettification. This results from a steep gradient in gravitational pull between the head and feet of an object, or person, stretching it into a long, thin shape as it approaches the singularity. In contrast, for a supermassive black hole, being several million to billion times the mass of the Sun, the tidal forces at the event horizon are less severe, allowing one to cross the boundary without immediate spaghettification, but this relative calm is short-lived as one moves deeper toward the center. The core of a black hole contains a singularity, a point where densities soar to infinity and the curvature of spacetime becomes infinite. According to general relativity, all matter and information entering a black hole inevitably collapse into this infinitely small point where gravitational forces are immeasurable. However, this depiction confronts the limits of general relativity, prompting numerous theoretical physicists to seek a unifying theory that incorporates quantum mechanics, often referred to as quantum gravity. Competing theories like string theory or loop quantum gravity endeavor to describe the singularity in terms of quantum mechanics, potentially replacing the singularity with a more comprehensible structural core. Beyond these internal dynamics, another perplexing question is the fate of information that crosses the event horizon. This leads to the so-called information paradox. Quantum mechanics posits that information is never truly lost, while the classical view of black holes suggests it is irretrievably destroyed within the singularity. To reconcile these differences, Stephen Hawking proposed that black holes emit radiation, now known as Hawking radiation, through quantum effects near the event horizon. This radiation could result in the gradual evaporation of black holes over cosmic timescales, suggesting that the information could be diffused back into the universe, albeit in an exceedingly altered state. This hypothesis is still a topic of vigorous debate and study, seeking to unify these apparent contradictions between the realms of quantum mechanics and general relativity. While our understanding of what transpires within a black hole remains incomplete and highly theoretical, current models portray it as a stage for extraordinary gravitational phenomena and extraordinary quantum effects. As research advances, we may edge closer to unraveling these mysteries, potentially discovering new realms of physics that transcend our current scientific boundaries. Black holes consume matter and energy from their surroundings through the process of accretion, a gravitationally driven mechanism that can transform seemingly empty space into regions of intense activity and light. The accretion process plays a crucial role in the growth and evolution of black holes, allowing them to gather mass from nearby stars, gas, and even light. When matter such as gas, dust, or stars ventures too close to a black hole, it becomes trapped by the black hole's extreme gravitational pull. Instead of plunging directly into the black hole, this material often forms an accretion disk, a swirling disk of matter spiraling inward. The matter in the disk experiences friction and compression, heating up to extremely high temperatures, sometimes reaching millions of degrees. This superheated material emits various forms of radiation, particularly in the X-ray spectrum, allowing astronomers to detect and study black holes, even though the black holes themselves emit no light. The intense gravitational gradient near the black hole ensures that the infalling matter loses angular momentum and energy, progressively spiraling closer to the event horizon. As the matter approaches the event horizon, relativistic effects become significant. The emitted radiation from this region is subject to gravitational redshift, whereby light is stretched to longer wavelengths, a phenomenon predicted by Einstein's theory of general relativity. This redshift serves as a powerful observational tool, providing clues about the behavior of matter in extreme gravitational fields. In addition to consuming matter from its immediate vicinity, black holes in binary systems can siphon material directly from a companion star. This happens when the star fills its Roche lobe, allowing matter to flow through the inner Lagrange point toward the black hole, forming an accretion stream. This stream feeds the accretion disk, leading to intensified radiation and energetic outbursts detectable across vast distances. The process is not entirely efficient, and some fraction of the accretion material is expelled from the black hole's vicinity in the form of powerful jets and winds. These jets, often observed in supermassive black holes at the centers of galaxies, can shoot out material at velocities approaching the speed of light, extending across thousands or even millions of light years. This phenomenon, known as relativistic jet emission, demonstrates the extraordinary power of black holes and their capacity to influence their cosmic environments. The resulting feedback, where the jets interact with the galaxy and intergalactic medium, can play a significant role in regulating galaxy formation and evolution. Black holes consume matter and energy through gravitationally driven accretion processes, forming highly energetic disks and jets. These mechanisms allow them to grow and exert significant influence over their surroundings, transforming in particular through the emission of high-energy radiation and powerful relativistic jets. Despite their profound gravitational pull, these processes let black holes escape their otherwise invisible nature, offering windows into the extreme physical conditions near their event horizons. Supermassive black holes residing at the centers of most galaxies, including our own Milky Way, are among the universe's most intriguing and enigmatic objects. Despite significant advances in astronomy and astrophysics, many mysteries still surround these colossal entities, from their origins to their roles in galactic evolution. One of the most profound mysteries is how supermassive black holes form and grow to their immense sizes, ranging from millions to billions of times the mass of our Sun. Two leading theories aim to explain their origins. One posits that supermassive black holes formed from the direct collapse of massive gas clouds in the early universe, bypassing the intermediate stages of star formation. The other theory suggests they grew from smaller seed black holes, which could have originated from massive stars or earlier generation star clusters, accumulating mass through the accretion of gas, dust, and mergers with other black holes. However, neither theory fully accounts for the presence of supermassive black holes in the very early universe, observed to exist just a few 100 million years after the Big Bang. The relationship between supermassive black holes and their host galaxies presents another profound puzzle. Observations have revealed a tight correlation between the mass of a supermassive black hole and the properties of the galactic bulge, such as the velocity dispersion of stars. This empirical relationship, known as the M-sigma relation, suggests that black holes and their host galaxies co-evolve. Yet the mechanisms driving this co-evolution remain unclear. Supermassive black holes significantly affect their environments, primarily through energetic feedback processes involving jets and radiation emitted from accretion disks. These processes can suppress or trigger star formation, regulate gas distribution, and sculpt galactic structures. Understanding these feedback mechanisms in detail is essential to developing a cohesive picture of galaxy formation and evolution. Additionally, the nature of the accretion processes near supermassive black holes continues to challenge our understanding. The physics governing the behavior of matter in the extreme gravitational and electromagnetic environments near black holes, including how some matter forms relativistic jets, remains a topic of active theoretical and observational research. Instruments like the Event Horizon Telescope, which provided the first direct image of a black hole's event horizon in 2019, are crucial for probing these extreme conditions and shedding light on the complex dynamics at play. Supermassive black holes also raise questions about the ultimate fate of galaxies. As galaxies merge, their central black holes are expected to form binaries and eventually coalesce into a single, more massive black hole. The detection of gravitational waves from such mergers, as observed by LIGO and Virgo, is beginning to provide insights into these cosmic events. However, direct observation and detailed understanding of the intermediate stages of black hole mergers offer a fertile ground for future discoveries. While we have made tremendous strides in observing and understanding supermassive black holes, many mysteries remain. From their formation and growth to their intricate relationship with their host galaxies and the dynamics of accretion and feedback processes, supermassive black holes continue to pose some of the most captivating questions in modern astrophysics. Ongoing and future observations, combined with sophisticated theoretical models, promise to deepen our understanding of these colossal enigmas and their role in shaping the universe. Black holes, by their very nature, emit no light and thus cannot be observed directly. However, scientists have developed ingenious methods to study these enigmatic objects indirectly, relying on their interactions with surrounding matter and the gravitational effects they exert on nearby objects. One of the most effective ways to observe black holes is by studying the X-ray emissions from their accretion disks. When matter from a companion star, interstellar gas, or other sources gets drawn toward a black hole, it forms a swirling accretion disk. As this matter spirals inward, it heats up due to friction and compression, reaching temperatures of millions of degrees. This hot material emits X-rays before crossing the event horizon. Space-based telescopes like NASA's Chandra X-ray Observatory, ESA's XMM Newton, and now the James Webb Space Telescope provide detailed observations of these high-energy emissions, revealing the presence and properties of black holes. Another crucial method involves observing the gravitational influence of black holes on nearby stars and gas clouds. For instance, astronomers can track the orbits of stars near the center of our galaxy, where the supermassive black hole Sagittarius A resides. By meticulously measuring these stellar orbits, scientists can infer the mass and the location of the black hole that is exerting the necessary gravitational force to govern such orbits. This technique was instrumental in providing compelling evidence for the existence of Sagittarius A*, earning the 2020 Nobel Prize in Physics for Reinhard Genzel and Andrea Ghez. Additionally, gravitational lensing provides another indirect method to study black holes. When a black hole passes between a distant light source, like a star or galaxy, and an observer on Earth, its immense gravitational field warps the space-time around it, bending and magnifying the light from the background object. This lensing effect can create multiple images or distortions of the light source, which scientists can analyze to gather information about the black hole's mass and properties. More recently, the detection of gravitational waves has opened a new avenue for studying black holes. Predicted by Einstein's general theory of relativity and first detected by the LIGO and Virgo observatories in 2015, gravitational waves are ripples in spacetime generated by the acceleration of massive objects, such as the merging of black holes. The wave patterns recorded by these observatories provide insights into the masses and spins of merging black holes, giving us a direct look at black hole interactions. Furthermore, the Event Horizon Telescope, EHT, represents a groundbreaking development in imaging the event horizon, the boundary beyond which nothing can escape a black hole's gravitational pull. In 2019, the EHT collaboration released the first-ever image of a black hole's shadow in the galaxy M87. This achievement relied on a global network of radio telescopes working in unison to simulate a planet-sized observatory, capable of resolving the fine details in the vicinity of a black hole. By analyzing the light bending and radiation near the event horizon, scientists can test predictions of general relativity and gain deeper insights into the nature of black holes. While direct observation of black holes is impossible due to their light-absorbing nature, scientists have developed a multitude of indirect methods to study them. By examining X-ray emissions, stellar dynamics, gravitational lensing effects, gravitational wave signals, and direct imaging of event horizons, researchers can unveil the properties and behaviors of these elusive cosmic giants, enriching our understanding of the universe. Hawking radiation, proposed by the eminent physicist Stephen Hawking in 1974, is a theoretical prediction that bridges the realms of quantum mechanics and general relativity, suggesting that black holes are not entirely black, but emit radiation. This groundbreaking concept has profound implications for our understanding of black holes and the fundamental principles of physics. Hawking radiation arises from the peculiarities of quantum field theory in the context of curved spacetime around a black hole. According to quantum mechanics, even in the vacuum of space, particle-antiparticle pairs continuously pop into and out of existence. Near the event horizon of a black hole, the intense gravitational field can separate these pairs. In some cases, one particle falls into the black hole while its counterpart escapes into space. The escaping particle appears as radiation emitted from the black hole. To an external observer, this phenomenon results in the gradual reduction of the black hole's mass and energy over time, a process that theoretically could lead to the black hole's eventual evaporation. The significance of Hawking radiation in black hole research is multifaceted. Firstly, it introduces the idea that black holes have a finite lifetime, challenging the notion of black holes as eternal, unchanging objects. The evaporation process is slow for massive black holes and rapid for smaller ones, suggesting that primordial black holes, formed shortly after the Big Bang, might have already evaporated completely or be in the final stages of their decay, potentially leaving observable effects that astronomers could detect. This theoretical radiation also touches on the heart of one of the most profound puzzles in modern physics, the information paradox. According to classical mechanics, any information about the matter that falls into a black hole is lost forever within the singularity. However, quantum mechanics insists that information cannot be destroyed. Hawking radiation suggests that, over immense timescales, information might be encoded in the radiation emitted from the black hole, thereby reconciling this apparent contradiction. While the exact mechanism for how information is preserved remains unclear, the hypothesis has spurred significant discussions and research efforts aimed at understanding the nature of information conservation in the universe. Moreover, Hawking radiation bridges the gap between quantum mechanics and general relativity, two pillars of modern physics that typically operate in very different regimes. By demonstrating that quantum effects can have macroscopic consequences in the strong gravitational fields of a black hole, Hawking's theory provides key insights into the quest for a unified theory of quantum gravity. Such a theory would encapsulate all fundamental forces in one framework, representing the ultimate goal of theoretical physics. Hawking radiation is not just a theoretical curiosity, but a significant cornerstone in our understanding of black holes. It reshapes our perception of these cosmic entities, hints at deeper principles governing the universe, and energizes the quest to reconcile the inconsistencies between quantum mechanics and general relativity, opening doors to new realms of discovery in the physics of the cosmos. Black holes, often viewed as the dark consumers of the cosmos, harbor potential for revolutionary applications in space travel and energy generation, albeit these ideas still hover within the domain of speculative science. Harnessing black holes, given their extreme gravitational and energetic properties, could radically transform our technological capabilities. One intriguing concept for space travel involves using rotating, or Kerr, black holes as cosmic shortcuts through spacetime. According to solutions of Einstein's field equations, a rotating black hole might possess a region known as the ergosphere, where spacetime is dragged around at high speeds. Some theories, most notably involving hypothetical constructs like wormholes, propose that Kerr black holes could form gateways between distant points in space and time. If traversable wormholes exist, they could potentially allow spacecraft to travel vast cosmic distances instantaneously by entering one end of the wormhole and emerging at another location in the universe. Such a mechanism, while currently beyond our technological reach and perhaps speculative, stimulates imagination about future possibilities. Developing technology capable of navigating and surviving the intense gravitational and tidal forces near a black hole remains a formidable challenge. Energy extraction from black holes, on the other hand, appears to be a more grounded possibility, leveraging phenomena like the Penrose process and Hawking radiation. The Penrose process, theorized by physicist Roger Penrose, suggests a method to extract energy from the ergosphere of a rotating black hole. In this process, an object or particle entering the ergosphere could split into two, with one part being consumed by the black hole while the other escapes. The escaping part could gain energy extracted from the black hole's rotational energy. This harvested energy, in theory, could be used for various applications, potentially offering an incredibly potent power source. Moreover, theoretical research into Hawking radiation posits another method of energy generation. As black holes slowly evaporate via Hawking radiation, they emit particles that carry away energy. Capturing this radiation could, hypothetically, provide a steady stream of energy. A more extreme idea involves creating microscopic black holes, which would evaporate much faster, providing intense bursts of energy. Some proposed scenarios involve particle accelerators or other advanced technologies to intentionally create and harness such micro-black holes for energy production. However, these notions face significant technological and safety hurdles before becoming feasible. In addition, black holes could theoretically power interstellar propulsion systems. One speculative idea involves the use of a black hole as a power source for a black hole bomb propulsion system. This involves placing a black hole within a massive reflecting shell that could amplify energy extracted from the black hole's rotational energy, creating a powerful thrust for propulsion. Science fiction has also explored concepts like the black hole starship, using controlled black holes as energy sources to propel spacecraft at relativistic speeds. While these ideas currently lie in the realm of theoretical speculation, ongoing advancements in our understanding of quantum mechanics, general relativity, and particle physics might bring some of these concepts closer to reality. Harnessing the power of black holes could revolutionize our energy systems and propel humanity toward an era of interstellar exploration, showcasing the potential of these mysterious cosmic objects to unlock extraordinary new capabilities in energy and space travel. Recent discoveries about black hole mergers have dramatically expanded our understanding of the universe in ways we couldn't have predicted. One of the most captivating findings emerged when the LIGO and Virgo observatories detected gravitational waves, those subtle ripples in the fabric of spacetime brought about by the collision of black holes. These events, which often involve black holes several times the mass of our Sun, unleash an unfathomable amount of energy, equivalent to several solar masses being converted directly into gravitational waves. The precision of these detections allows scientists to confirm the existence of intermediate mass black holes, which fill in the long-standing gap between small stellar mass black holes and the supermassive ones found at the centers of galaxies. Equally exciting are the broader implications for our understanding of the cosmos. Black hole mergers serve as natural laboratories for testing Einstein's theory of general relativity under extreme conditions. Recent findings hint at the possibility that these mergers might not always produce a perfect ring-down or settling of the newly formed black hole, suggesting there might be more exotic physics at play. Additionally, these events are key to solving the mystery of heavy element formation. The intense gravitational interactions and resulting high-energy phenomena have been proposed as sites where elements heavier than iron could be forged, something stellar nucleosynthesis alone struggles to fully explain. The continuous observation and analysis of such cosmic phenomena could potentially unlock answers to some of the universe's most profound mysteries, reshaping our understanding of its very fabric. Dark matter is an elusive and mysterious substance that does not emit, reflect, or absorb light, making it invisible to current telescopes. Despite its invisibility, it exerts a gravitational pull, influencing the motion of galaxies and galaxy clusters. In fact, about 85% of the universe's total mass is thought to be comprised of dark matter, suggesting that the ordinary matter we see, from stars to planets, makes up only a minor fraction of the cosmos. The discovery of dark matter traces back to the early 20th century. In the 1930s, Swiss astronomer Fritz Zwicky observed the Coma cluster of galaxies and found that the galaxies were moving too rapidly to be held together by just the visible matter. He coined the term Dunkel Materie, meaning dark matter, to describe this unseen mass. Further compelling evidence was provided by Vera Rubin in the 1970s when she studied the rotation curves of spiral galaxies. Rubin found that stars at the outer edges of galaxies were rotating just as quickly as those near the center, a phenomenon that couldn't be explained by the presence of visible matter alone. This suggested that a significant amount of unseen mass was present, exerting a gravitational force. Modern technological advancements continue to shed light on dark matter, albeit indirectly. Observatories like the Hubble Space Telescope have offered insights through gravitational lensing, where the light from distant galaxies is bent by massive invisible objects between them and us. Even though scientists have yet to directly detect dark matter particles, numerous experiments are underway to identify what dark matter is actually made of, with hypotheses ranging from WIMPs, weakly interacting massive particles, to axions. Understanding dark matter remains one of the most pressing and tantalizing challenges in cosmology today, promising to revise our comprehension of the universe's structure and evolution. Dark matter plays a pivotal role in shaping the structure of the universe on both grand and local scales. Its influence is omnipresent, sculpting the cosmos from the formation of galaxies to the behavior of entire galaxy clusters. Due to its invisible nature, dark matter's presence is inferred through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. In the early universe, shortly after the Big Bang, dark matter acted as a cosmic scaffold around which ordinary matter could gather. This scaffolding facilitated the formation of the first galaxies and galaxy clusters. Without the gravitational pull of dark matter, the gas needed to form stars and galaxies would not have clumped together as efficiently. The so-called cosmic web, an immense network of filaments made primarily of dark matter linking galaxies and clusters, demonstrates how dark matter organizes matter on the largest scales. These dark matter filaments attract ordinary matter, guiding the formation and distribution of galaxies and intergalactic gas along their lengths. On a smaller scale, dark matter also influences the internal dynamics of galaxies. Observations of the rotation curves of spiral galaxies, where stars at the outer edges rotate faster than predicted by visible mass alone, indicate the presence of vast amounts of unseen mass, dark matter, extending well beyond the visible edges of these galaxies. This invisible halo of dark matter stabilizes galaxies, preventing them from tearing apart due to their rapid rotation. Consequently, dark matter is fundamental in the formation, structure, and ultimate fate of the universe. Understanding its properties and interactions remains one of cosmology's most compelling quests. As we uncover more about dark matter, we will inevitably gain deeper insights into the evolution of cosmic structures and the very makeup of the universe, potentially revealing new realms of physics beyond our current knowledge. Detecting dark matter, given its elusive nature, is one of the most intriguing challenges in modern science. Because dark matter does not emit, absorb, or reflect light, scientists rely on indirect methods to infer its presence and properties. One primary avenue of detection involves observing its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Gravitational lensing is a powerful tool in the detection of dark matter. When light from distant galaxies passes through a cluster of galaxies, the immense gravitational field of the cluster, which includes a significant component of dark matter, bends the light, distorting and magnifying the images of the background galaxies. By mapping these distortions, astronomers can infer the distribution and amount of dark matter within the cluster. The lensing effects often reveal more mass than what is visible, indicating the presence of dark matter. Another method hinges on the rotation curves of galaxies. When astronomers like Vera Rubin studied the rotational speeds of stars in spiral galaxies, they found that stars at the outer edges of these galaxies were rotating as fast as those near the center, defying expectations based solely on observable matter. This uniform rotation speed suggests the existence of a dark matter halo enveloping the galaxies, providing the extra gravitational pull needed to keep the stars in such rapid motion. On a more experimental front, scientists are utilizing underground detectors to capture potential dark matter particles. These direct detection experiments, like those involving cryogenic detectors or liquid xenon targets in facilities such as the Large Underground Xenon (LUX) experiment, seek to observe the rare interactions between dark matter particles and regular matter. When a dark matter particle collides with a nucleus in the detector, it can produce a minuscule amount of energy in the form of light or heat, which sophisticated instruments can detect. Finally, particle accelerators like the Large Hadron Collider (LHC) at CERN probe the existence of dark matter by smashing protons together at high energies. The collisions might produce dark matter particles, which could be inferred from missing energy and momentum in the resulting particle tracks. Though dark matter has not yet been directly observed, these methods provide compelling evidence of its existence and continue to narrow down its possible properties. The quest to detect dark matter directly remains a captivating frontier in the ever-evolving field of cosmology, promising to unlock new dimensions of our understanding of the universe. The composition of dark matter remains one of the most tantalizing mysteries in cosmology, and several leading theories have emerged to explain its elusive nature. One of the most prevalent theories posits that dark matter consists of WIMPs, or weakly interacting massive particles. These hypothetical particles are thought to have been produced in large quantities during the early universe and could account for the vast amount of unseen mass based on their weak interactions with normal matter and electromagnetic radiation. WIMPs are appealing because they fit well within the framework of the standard model of particle physics and its extensions, such as supersymmetry, which predicts the existence of such particles. Another compelling candidate is the axion, a particle first proposed in the late 1970s as a solution to the strong CP problem in quantum chromodynamics. Axions, if they exist, would be extremely light and interact very weakly with ordinary matter, making them difficult to detect. They could be produced in the early universe in sufficient quantities to account for dark matter and are being actively searched for in experiments such as the Axion Dark Matter Experiment, ADMX, and other initiatives. Sterile neutrinos are another intriguing possibility. Unlike the known active neutrinos, which interact via the weak nuclear force, sterile neutrinos would interact only through gravity. Their mass could help explain the observed properties of dark matter, and they might also play a role in the formation of large-scale structures in the universe. The detection of sterile neutrinos would have profound implications for our understanding of both dark matter and particle physics. There are also more exotic theories, such as the notion of dark matter being composed of primordial black holes. These black holes could have formed during the very early stages of the universe due to extreme density fluctuations. Although challenging to detect, they could contribute to the gravitational effects attributed to dark matter. Additionally, there are theories suggesting that dark matter might not be composed of particles at all, but instead could be a modification of the known laws of gravity. One such theory is modified Newtonian dynamics, MOND, which proposes changes to Newton's laws on cosmic scales to account for the missing mass in the universe. However, this idea is less favored because it struggles to explain observations on multiple scales as comprehensively as the particle-based dark matter theories. Each of these theories is the subject of rigorous experimental and observational scrutiny. Progress in this area not only promises to solve the enigma of dark matter, but also has the potential to unveil new physics that could revolutionize our understanding of the universe. Dark energy and dark matter are two of the most enigmatic components of our universe, each playing a distinct and pivotal role in its evolution, yet they differ fundamentally in their nature and effects. Together, they constitute approximately 95% of the universe, with dark energy making up around 70% and dark matter about 25%. Dark matter is a form of unseen mass that exerts gravitational forces, contributing to the formation and clustering of galaxies and galaxy clusters. Its gravitational influence helps keep galaxies intact by providing the additional mass necessary to explain the observed rotation speeds of stars at the outskirts of these galaxies. Though it does not interact with electromagnetic forces, making it invisible to light, dark matter still clumps together under the force of gravity, guiding the formation of large-scale cosmic structures in the universe. In stark contrast, dark energy is a mysterious force that appears to drive the accelerated expansion of the universe. First inferred in the late 1990s through observations of distant Type Ia supernovae, dark energy acts as a sort of anti-gravity, counteracting the attractive force of gravity on cosmic scales. Unlike dark matter, which clusters together, dark energy is thought to be uniformly distributed throughout space, affecting the universe's geometry and its rate of expansion. The nature of dark energy remains one of the central puzzles in modern cosmology, and it is often modeled through the cosmological constant, a term introduced by Einstein, or through more dynamic fields such as quintessence. The effects of dark energy are most evident when looking at the universe's large-scale structure and its accelerated expansion rate. It stretches space itself, influencing the rate at which galaxies move apart from one another. This accelerating expansion poses profound implications for the universe's future, suggesting that it could continue to expand forever, leading to a cold, dark, and increasingly diffuse cosmos. While dark matter binds galaxies and clusters together through its gravitational pull, dark energy drives them apart, dominating the dynamical evolution of the universe on the largest scales. Understanding both phenomena is crucial for a complete picture of the universe's origin, structure, and ultimate fate. Researchers continue to employ a range of observational strategies, including cosmic microwave background measurements, large-scale galaxy surveys, and gravitational lensing studies to probe these dark components and unravel the mysteries they present. Dark energy exerts a profound influence on the expansion of the universe, acting as a mysterious force that accelerates this expansion. This discovery, which upended previous notions of a decelerating cosmic expansion, emerged from observations of distant Type Ia supernovae in the late 1990s. These supernovae, considered standard candles because of their consistent intrinsic brightness, allowed astronomers to measure the distances to far-off galaxies. They discovered that galaxies were not just moving away from us, but were accelerating in their recession, implying that some unknown force was pushing them apart with increasing speed. The role of dark energy in the universe's accelerated expansion can be understood through its effect on spacetime itself. Unlike ordinary matter and dark matter, which clump together and exert gravitational attraction, dark energy is believed to have a repulsive effect. It is uniformly distributed across the universe, resulting in a constant energy density even as space expands. This characteristic can be modeled as a cosmological constant, denoted by the Greek letter lambda, in Einstein's field equations of general relativity, signifying a form of vacuum energy that permeates all of space. As dark energy dominates the universe's energy content, its repulsive force overwhelms the gravitational pull of matter. This causes the fabric of spacetime to stretch, accelerating the rate at which the universe expands. Current measurements suggest that dark energy makes up about 70% of the total energy content of the universe, leading to an accelerating expansion that was initially counterintuitive to many cosmologists. The implications of this accelerated expansion are profound. Over time, galaxies will move farther apart, and the observable universe will grow increasingly isolated. This phenomenon might lead to a big freeze scenario, where galaxies recede beyond the horizon and become unobservable, stars burn out, and the universe cools to the point where thermodynamic activity ceases. Another intriguing possibility is the Big Rip, a far-future event where the influence of dark energy grows so strong that it eventually tears apart galaxies, stars, and even atomic structures. Research efforts are ongoing to better understand dark energy, utilizing methods such as studying the cosmic microwave background radiation, analyzing large-scale galaxy surveys, and observing the effects of gravitational lensing. By gaining insights into the nature of dark energy, scientists hope to unlock deeper truths about the fundamental forces shaping our cosmos and perhaps unveil new realms of physics that lie beyond our current understanding. The most compelling pieces of evidence for dark energy's existence arise from diverse astronomical observations and measurements that consistently indicate the universe's accelerated expansion. These lines of evidence collectively paint a coherent picture of dark energy as a dominant force in the cosmos. One of the first and most persuasive pieces of evidence came from the study of distant Type Ia supernovae. In the late 1990s, two independent research teams, the Supernova Cosmology Project and the High Z Supernova Search Team, observed these supernovae as standard candles, owing to their uniform intrinsic brightness. By measuring their apparent brightness and redshift, scientists discovered that distant supernovae were systematically dimmer than expected. This dimming suggested that the universe's expansion rate has been accelerating over the past several billion years, implying the presence of a repulsive force, dubbed dark energy, counteracting gravity. Another significant line of evidence comes from the cosmic microwave background, CMB radiation, the afterglow of the Big Bang. The Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have measured the CMB with unprecedented precision. The data reveal tiny temperature fluctuations that provide a snapshot of the early universe. By analyzing these fluctuations, scientists can infer the universe's geometry and its overall energy content. The CMB measurements indicate that the universe is flat, implying a specific total energy density. However, visible matter, dark matter, and radiation together account for only about 30% of this density, suggesting that the remaining 70% must be due to dark energy. Large-scale structure surveys of galaxies offer additional support. Projects such as the Sloan Digital Sky Survey, SDSS, map the distribution of galaxies across the universe. These surveys help trace the universe's large-scale structure and the clustering patterns of galaxies. Observations show that galaxies are not only moving away from each other, but doing so at an accelerating pace. This acceleration aligns well with the presence of dark energy. Further evidence comes from the phenomenon of baryon acoustic oscillations, BAO. In the early universe, pressure waves propagated through the hot plasma, leaving imprints in the distribution of galaxies. These imprints, or acoustic peaks, act as a cosmic yardstick. By measuring the distance between these peaks in the galaxy distribution, astronomers can track the expansion history of the universe. BAO measurements are consistent with an accelerating universe driven by dark energy. Lastly, gravitational lensing studies, where the light from distant objects is bent by massive foreground structures, also provide evidence. By examining how galaxies and galaxy clusters warp the light from background sources, scientists can infer the distribution of both dark matter and dark energy. The results support a model of the universe dominated by dark energy that influences the overall mass-energy balance and the expansion rate. Collectively, these diverse and converging lines of evidence make a robust case for the existence of dark energy, profoundly shaping our understanding of cosmology and the universe's evolution. The potential interaction between dark matter and dark energy is a topic that delves into some of the deepest questions about the universe's composition and evolution. While both are crucial to our understanding of cosmology, they possess fundamentally different properties and roles. Dark matter, with its gravitational clumping, acts as the backbone for cosmic structures, whereas dark energy drives the accelerated expansion of the universe. In the current cosmological model, the standard lambda cold dark matter (LCDM) model, dark matter and dark energy are usually considered to be distinct and non-interacting components. Dark matter contributes to the formation and stability of galaxies and clusters through its gravitational pull, whereas dark energy, often modeled as a cosmological constant, lambda, exerts a uniform repulsive force throughout space, driving cosmic acceleration. However, some theoretical models hypothesize potential interactions between dark matter and dark energy. These interactions could modify the behaviors of both components over cosmic time. One such model involves the notion of coupled dark energy, where the dark energy density varies over time, potentially interacting with dark matter in a way that alters its properties or distribution. For instance, dark energy might decay into dark matter particles or vice versa, affecting the relative abundances and distributions of these substances in the universe. Another interesting model is scalar field dark energy, where dark energy is described by a dynamic scalar field rather than a constant value. In these models, the scalar field could interact with dark matter, influencing its clustering behavior and the overall dynamics of cosmic structures. This interaction might lead to observable signatures in the large-scale structure of the universe, such as modifications in the clustering of galaxies or deviations in the cosmic microwave background radiation. Experimental and observational efforts have not yet provided definitive evidence for such interactions. However, precise measurements of the cosmic microwave background, galaxy clustering, baryon acoustic oscillations, and the distribution of large-scale structures continue to offer insights. For example, deviations from the expected behavior in these observations might hint at interactions between dark matter and dark energy. Another avenue of exploration is high-energy particle physics experiments, which might uncover new particles or forces that could mediate interactions between dark matter and dark energy. Experiments at facilities like the Large Hadron Collider, LHC, and various dark matter detection experiments could provide indirect evidence for such interactions by identifying anomalies that cannot be explained by the current model. While the standard cosmological model currently treats dark matter and dark energy as independent, conceptual models and ongoing research explore the possibility of their interaction. Detecting any such interactions would significantly enhance our understanding of these mysterious components and might lead to revolutionary changes in our comprehension of the universe's fundamental forces and the underlying physics. Understanding the true nature of dark energy presents a multitude of challenges, both observational and theoretical, that scientists are striving to overcome. These challenges are rooted in the elusive properties of dark energy and the limitations of our current models and technology. One of the foremost challenges is its detection and direct measurement. Unlike dark matter, which exerts gravitational forces observable through its effects on galaxies and cosmic structures, dark energy's influence is more subtle, manifesting primarily in the accelerated expansion of the universe. This acceleration is inferred from indirect observations, such as the redshifts of distant type Ia supernovae and the patterns in the cosmic microwave background radiation. These methods, while robust, do not provide a direct measure of dark energy itself, leaving its nature somewhat ambiguous. Adding to the complexity is the fact that dark energy constitutes about 70% of the universe's energy density, yet it remains uniformly distributed and does not clump like ordinary matter or dark matter. This large-scale uniformity makes it difficult to isolate specific regions of space where dark energy's effects can be individually studied, complicating the design of experiments capable of probing its properties. From a theoretical standpoint, integrating dark energy into the existing framework of physics poses significant difficulties. The most commonly used model, the cosmological constant, lambda, represents dark energy as a constant vacuum energy density. This model, while fitting current observations, suffers from the cosmological constant problem. This problem arises because the predicted value of the vacuum energy from quantum mechanics is vastly larger than what is observed. Bridging this enormous discrepancy remains one of the deepest unsolved problems in theoretical physics. Alternative theories suggest that dark energy could be a dynamic field, such as quintessence. This field would vary over time and space, potentially interacting with other cosmic components such as dark matter. However, these models introduce additional parameters and complexities, making them harder to test and validate against observations. Moreover, theoretical tools needed to fully describe these dynamic fields often require extensions to the standard model of particle physics or modifications to general relativity, creating tension with well-established physical laws. Precision in cosmological measurements also poses a challenge. Observing the universe with the required accuracy to constrain dark energy's properties demands next-generation telescopes and instruments. Projects like the Dark Energy Survey, DES, and the Euclid mission are designed to map large portions of the sky with high precision, but interpreting the data from these massive surveys requires sophisticated statistical tools and deep theoretical understanding. Lastly, reconciling dark energy with other fundamental forces and particles might necessitate new physics beyond the current paradigms. This could involve extra dimensions, modifications of Einstein's theory of gravity, such as FR gravity or scalar tensor theories, or entirely new particle species and interactions. Developing and testing these ideas remains a formidable task, requiring advancements in both experimental technology and theoretical frameworks. The quest to understand dark energy is hampered by its indirect detectability, the theoretical challenges of incorporating it into established physics, the need for precise cosmological measurements, and the potential requirement for new physics. Despite these hurdles, ongoing research holds the promise of unraveling this profound mystery, with each new observation and experiment bringing us one step closer to comprehending the true nature of dark energy. The influence of dark matter and dark energy extends far beyond their roles in shaping the cosmos's large-scale structures. These mysterious components also significantly impact the universe's ultimate fate. Understanding their interplay is essential for predicting how the universe will evolve and what it might eventually become. Dark matter, which constitutes approximately 25% of the universe's energy density, acts as the primary gravitational scaffold around which galaxies and galaxy clusters form. Its gravitational pull helps to bind these cosmic structures together, counteracting the dispersive effects of the universe's expansion. The presence of dark matter has allowed galaxies to coalesce and persist over billions of years, forming the rich and varied cosmic landscape we observe today. In contrast, dark energy, making up about 70% of the universe's energy density, functions as a repulsive force driving the universe's accelerated expansion. Its influence became apparent through observations of distant Type Ia supernovae in the late 1990s, which indicated that the universe's expansion rate is not slowing down, but rather speeding up. This acceleration suggests that dark energy works against gravity, causing space itself to stretch at an increasing rate. The balance between dark matter and dark energy will ultimately determine the universe's fate. If dark energy continues to dominate, the expansion will accelerate indefinitely, leading to what is often called the Big Freeze or heat death. In this scenario, galaxies will drift further apart, stars will burn out, and the universe will become an increasingly cold and dark place as it expands. Over trillions of years, the remaining cosmic structures will become isolated, with any residual heat dissipating, leading to a state of thermodynamic equilibrium where no significant physical processes occur. An even more extreme possibility is the Big Rip scenario. If the repulsive force of dark energy grows stronger over time, contrary to the current cosmological constant model, the acceleration could increase to the point where it tears apart galaxies, stars, planets, and eventually even atomic structures, disintegrating all matter in the universe. This would culminate in a cataclysmic end where space-time itself is ripped apart. Conversely, if dark matter or a future understanding of dark energy reveals some new physics that counterbalances this acceleration, the universe might reach a stable state or even undergo a big crunch. In this scenario, the expansion would eventually halt and reverse, leading to a contraction that culminates in a singularity, possibly followed by a new Big Bang, according to some speculative models. Additionally, theoretical models exploring dynamic forms of dark energy, such as quintessence, introduce more nuanced possibilities. These include oscillating universes where periods of expansion and contraction follow each other in cycles, or scenarios where dark energy diminishes over time, allowing gravitational forces to reclaim dominance. Current observations and cosmological data, such as the cosmic microwave background radiation, large-scale structure surveys, and supernova measurements, strongly support a future dominated by dark energy and an accelerating expansion. However, as research continues, our understanding of these dark components may evolve, potentially revealing new insights and altering our long-term predictions for the universe. While dark matter binds the cosmos together through its gravitational influence, dark energy drives its accelerated expansion. The balance between these forces not only shapes the universe's present structure, but also dictates its future trajectory, presenting varied and profound possibilities, from an ever-expanding cosmos heading toward a cold, dark fate, to more dramatic and speculative outcomes. The formation and evolution of the Milky Way galaxy are processes that span billions of years, offering a fascinating glimpse into the complex mechanisms that shape galaxies. The Milky Way formed approximately 13.6 billion years ago, not long after the Big Bang, through a series of hierarchical mergers and accretions of smaller gas clouds and proto-galaxies. Initially, small overdensities in the matter distribution of the early universe began to collapse under their own gravity, forming primordial dark matter halos. These halos served as the gravitational scaffolds around which gas and dust gathered, cooling and condensing to form the first stars and star clusters. Over time, these early star-forming regions merged and coalesced, gradually building up larger structures. Some of these early stars, known as Population 3 stars, were massive and short-lived, ending their lives in supernova explosions that enriched the surrounding gas with heavier elements, setting the stage for subsequent generations of star formation. The Milky Way's evolution was notably influenced by its interactions and mergers with other galaxies. These hierarchical mergers are a fundamental aspect of the LCDM, Lambda Cold Dark Matter cosmological model, which describes how structures in the universe form and grow. As the Milky Way's progenitor galaxy accreted smaller systems, it grew in size and complexity. This process also led to the formation of its halo, a spherical distribution of older stars and globular clusters enveloping the galaxy. Evidence of past mergers can be seen in features like stellar streams, which are remnants of smaller galaxies that were tidally disrupted and absorbed by the Milky Way. The Milky Way's thin disk, where most of its stars, including those in the spiral arms, are located, formed about 8 to 10 billion years ago. This disk emerged from the gravitational collapse of gas that settled into a rotating disk structure. Active star formation within the disk created new generations of stars, including population 1 stars, which are rich in heavier elements. The ongoing formation of stars in the Milky Way's disk is sustained by gas accretion from the intergalactic medium and the infall of smaller satellite galaxies. One notable feature of the Milky Way is its spiral structure, characterized by distinct spiral arms that house a significant fraction of the galaxy's star-forming regions. The spiral arms are thought to be density waves, regions of higher density that propagate through the disk, triggering the collapse of gas clouds and the formation of new stars. These arms play a crucial role in the ongoing star formation and the dynamical evolution of the galaxy. The central bulge of the Milky Way, populated by older stars and containing a supermassive black hole known as Sagittarius A*, is another key component. The bulge likely formed through a combination of early rapid star formation and subsequent mergers that funneled stars and gas toward the galaxy's center. Over time, dynamical processes like bar formation and secular evolution also contributed to shaping the bulge. The Milky Way continues to evolve, interacting with its satellite galaxies, such as the Large and Small Magellanic Clouds, and absorbing smaller systems through tidal interactions. These interactions influence the Milky Way's structure and star formation activity, enriching its stellar population and contributing to its growth. The Milky Way's formation and evolution are complex processes driven by hierarchical mergers, gas accretion, star formation, and dynamical interactions. From its origins in the early universe to its current structure as a majestic spiral galaxy, the Milky Way's history encapsulates the rich and dynamic nature of galaxy formation and evolution, offering insights into the broader processes that shape our cosmic environment. The supermassive black hole at the center of the Milky Way, known as Sagittarius A*, pronounced Sagittarius A star, is a subject of intense study and fascination, surrounded by numerous mysteries and unanswered questions. Discovered in the 1970s through radio observations, this enigmatic behemoth has an estimated mass of about 4 million times that of our Sun. Despite extensive research, many aspects of its nature and behavior remain puzzling to astronomers and physicists. One of the primary mysteries involves understanding how Sagittarius A** and other supermassive black holes form and grow to such enormous sizes. While it's believed that they might originate from the collapse of massive gas clouds or the merger of smaller black holes, the exact mechanisms and timescales for their growth are not well understood. Observations suggest that supermassive black holes exist in the centers of most galaxies, indicating a fundamental role in galaxy formation and evolution, yet the details of this relationship are still unclear. Another intriguing mystery is the relatively quiescent nature of Sagittarius A*, compared to the supermassive black holes in active galactic nuclei, AGNs, or quasars, which emit vast amounts of energy as they accrete matter, Sagittarius. A* is unusually quiet. While it occasionally flares up, emitting X-rays and other radiation, these events are infrequent and far less energetic than those observed in more active galactic centers. Understanding why Sagittarius A* is not as active raises questions about the availability of surrounding material for accretion and the physical processes governing its behavior. The precise dynamics and environment surrounding Sagittarius A* also pose challenges. The region around the black hole, known as the galactic center, is densely populated with stars, dust, and gas. The orbits of stars near Sagittarius A*, particularly the so-called S stars, provide crucial data for measuring the black hole's mass and for testing predictions of Einstein's general relativity in strong gravitational fields. However, the complex interplay of gravitational forces, magnetic fields, and stellar interactions in this crowded region makes it difficult to build a comprehensive model of this environment. Furthermore, there are questions about the event horizon of Sagittarius A*, the boundary beyond which nothing can escape its gravitational pull. The Event Horizon Telescope (EHT) collaboration aims to capture images of the shadow or silhouette of the event horizon, providing direct evidence of its existence. While initial images of the black hole in the nearby galaxy M87 have been obtained, capturing similar images of Sagittarius A asterisk proves more challenging due to the interstellar material obscuring our view and the rapid variability of the accretion flow around the black hole. Additionally, the role of Sagittarius A asterisk in influencing the Milky Way's structure and dynamics remains an open question. While it's known that supermassive black holes have significant gravitational impacts on their host galaxies, the exact ways in which Sagittarius A asterisk affects star formation, galactic rotation, and the overall evolutionary trajectory of the Milky Way are topics of ongoing research. Finally, exploring the quantum properties of black holes, such as Hawking radiation, a theoretical prediction that black holes emit radiation due to quantum effects near the event horizon, remains speculative for Sagittarius A asterisk given current observational limitations. Detecting such effects would require highly sensitive instruments and could revolutionize our understanding of black hole thermodynamics and quantum gravity. The supermassive black hole at the center of the Milky Way, Sagittarius A asterisk, continues to be a profound source of scientific mystery. Its formation, growth, quiescent nature, environment, event horizon characteristics, and broader influence on galactic dynamics constitute some of the foremost questions driving current astrophysical research. Solving these mysteries will provide deeper insights into not only Sagittarius A asterisk, but also the fundamental properties and behaviors of black holes throughout the universe. Galaxy collisions play a transformative role in the structure and evolution of galaxies, profoundly impacting their morphology, star formation activity, and overall dynamics. These interactions are relatively common in the universe and are crucial processes that drive the recycling and redistribution of matter and energy within galaxies. One of the most dramatic effects of galaxy collisions is the alteration of galaxy morphology. When two galaxies collide, their mutual gravitational interactions can distort their shapes, leading to the formation of tidal tails, bridges, and shells. These features arise due to the gravitational forces stretching and pulling the stars and gas in the interacting galaxies. For example, the iconic antennae galaxies display long, sweeping tidal tails formed by their interaction. Over time, the galaxies may merge, resulting in a remnant galaxy with a morphology that could differ significantly from the progenitors. This process can transform spiral galaxies into elliptical galaxies, as seen in many massive evolved galaxy clusters where ellipticals dominate. Collisions also trigger bursts of star formation, known as starbursts, as the gas clouds within the galaxies are compressed and shocked by the interaction. This heightened gas density leads to the rapid formation of new stars. The increased star formation activity can result in brilliant starburst regions, contributing to the overall luminosity of the merging system. The Milky Way and Andromeda galaxies are on a collision course, expected to merge in about 4.5 billion years, and this event will likely trigger extensive star formation as well. Another consequence of galaxy collisions is the fueling and activation of supermassive black holes within the galactic centers. As gas and dust are funneled towards the central regions during a merger, they can accrete onto the supermassive black holes, igniting active galactic nuclei, AGNs, and potentially transforming a quiescent galaxy into a luminous quasar. This intense activity not only affects the central black holes, but also drives powerful outflows and jets that can influence the entire galaxy, regulating further star formation and redistributing material. Galaxy collisions also impact the distribution and properties of dark matter halos surrounding galaxies. During interactions, the dark matter halos can merge and relax into a new equilibrium, affecting the gravitational potential and dynamics of the resultant galaxy. The combined dark matter halo provides the necessary gravitational binding to hold the newly formed galaxy together. Additionally, mergers and collisions influence the growth and evolution of galaxy clusters. As galaxies within clusters interact and merge, the cluster evolves into larger, more massive systems. The ongoing interactions within clusters contribute to their complex structure and the distribution of intra-cluster gas observed in X-ray wavelengths. Theoretical models and simulations, such as those performed using powerful supercomputers, have been instrumental in understanding the complex dynamics of galaxy collisions. These simulations help astronomers visualize the stages of interaction, predict resulting structures, and compare them with observational data to validate current theories of galaxy evolution. Overall, galaxy collisions are catalysts for significant structural and evolutionary changes. They mold galaxies into new forms, trigger star formation and AGN activity, redistribute dark matter, and drive the growth of large-scale cosmic structures. Through these interactions, galaxies continuously evolve, enriching the universe with dynamic and diverse structures. Understanding galaxy collisions thus provides vital insights into the fundamental processes that shape the cosmos. The Andromeda Galaxy, also known as M31, is the closest spiral galaxy to the Milky Way and one of the most studied objects in the sky. Despite its relative proximity and extensive research, the Andromeda Galaxy harbors several mysterious features that continue to intrigue astronomers. One of the most puzzling aspects of Andromeda is its double nucleus. Observations have revealed that the galaxy's central region contains not one but two closely spaced bright cores. One potential explanation for this phenomenon is that the galaxy's double nucleus may result from the presence of a supermassive black hole offset from the true center due to past interactions with a smaller galaxy. Alternatively, it could be a sign of a complex dynamical process involving stars orbiting a central black hole, creating an illusion of duality. Another area of study is the unusual population of Andromeda's globular clusters. The galaxy contains a surprisingly high number of these ancient star clusters compared to the Milky Way. This abundance raises questions about the history of Andromeda's formation and its past interactions with other galaxies, which may have stripped globular clusters from smaller systems or induced star formation in the galactic halo. The halo of Andromeda itself is also a subject of fascination. The extended halo is populated with numerous faint stars and star streams, remnants of smaller galaxies torn apart and absorbed by Andromeda over billions of years. These streams provide a history of galactic mergers and interactions, yet their full extent and the detailed history remain mysterious. Further mapping of these streams using deep sky surveys will help unravel Andromeda's past and the role such interactions have played in shaping its current structure. Another enigmatic feature is the prominent ring-like structure observed in the galaxy's disk. Discovered in far ultraviolet images, this ring could be a result of a past collision with a smaller galaxy or an ongoing interaction that has induced ring-like star formation. Understanding the origin of this ring could reveal insights into the dynamical processes and past events that have influenced the Andromeda Galaxy. Moreover, the dark matter halo of Andromeda presents its own set of mysteries. While it is known that Andromeda, like most galaxies, contains a substantial amount of dark matter, the precise distribution and density profile of this dark matter halo are subjects of ongoing research. Observations and simulations aim to provide a clearer picture of how dark matter contributes to the galaxy's gravitational potential and overall structure. The eventual collision between the Milky Way and Andromeda, predicted to occur in about 4.5 billion years, adds another layer of intrigue. While this future event falls outside the classical study of Andromeda's current features, understanding the dynamics and orbital pathways leading up to this colossal merger helps inform predictions about the future combined galaxy's structure and the fate of their constituent stars and planetary systems. Finally, studying Andromeda's supermassive black hole, with an estimated mass of about 100 million times that of the Sun, is a key area of interest. While it is less active than the supermassive black holes found in quasars, investigating how it influences the surrounding stellar populations and its role in the galaxy's evolution remains an open question. The Andromeda Galaxy's double nucleus, abundant globular clusters, halo features, ring structures, dark matter distribution, and impending collision with the Milky Way all represent compelling mysteries. Ongoing observations and theoretical modeling continue to deepen our understanding of these enigmatic elements, enhancing our broader comprehension of galactic formation, evolution, and dynamics. Scientists utilize an array of sophisticated techniques to study the large-scale structure of the universe, often referred to as the cosmic web. One foundational method involves astronomical surveys which map the distribution of galaxies across vast expanses of space. Instruments like the Sloan Digital Sky Survey have been pivotal, compiling data on millions of galaxies to reveal the intricate patterns of cosmic filaments and voids. The light from these distant galaxies takes millions or even billions of years to reach us, serving as a time machine that allows astronomers to peer back into different epochs of the universe's history. With this information, they can trace the formation and evolution of cosmic structures from near the Big Bang to the present day. In addition to optical surveys, scientists also employ radio telescopes to detect neutral hydrogen gas, which can outline the cosmic web's filaments even in regions where galaxies are sparse. Advanced simulations on supercomputers play a crucial role as well, allowing researchers to model the gravitational dynamics of dark matter and the baryonic matter it influences. By comparing these simulations with observational data, scientists can test and refine theories about the universe's composition, including the elusive dark matter and dark energy that govern its expansion. Employing a blend of observational data and computational models, they strive to unravel the mysteries of the immense and complex structure we are a part of. Quasars, or quasi-stellar objects, are among the most luminous and enigmatic entities in the universe. At the heart of these celestial powerhouses lies a supermassive black hole with masses ranging from millions to billions of times that of our Sun. This black hole accretes surrounding gas and dust, creating an extremely hot and dense accretion disk. As matter spirals into the black hole, it heats up to temperatures exceeding millions of degrees, emitting an extraordinary amount of energy across the electromagnetic spectrum, from radio waves to visible light to X-rays. It's this intense radiation that makes quasars visible even from billions of light-years away, offering a glimpse into the early universe. What makes quasars particularly mysterious is the sheer scale of their energy output and the mechanisms driving it. A single quasar can outshine an entire galaxy of stars, yet it is confined to a region no larger than our solar system. This poses questions about the efficiency of energy transfer in such extreme conditions. Additionally, quasars vary in brightness over relatively short timescales, leading scientists to probe the chaotic environments near the event horizons of supermassive black holes. Understanding quasars not only sheds light on the behavior of matter under extreme gravitational forces, but also provides clues about galaxy formation and the evolution of the cosmos itself. Galaxy clusters, the largest gravitationally bound structures in the universe, are formed through a process that spans billions of years and involves the convergence of smaller groups of galaxies. Initially, small fluctuations in the density of matter in the early universe, rendered by the Big Bang's aftermath, began to attract additional matter through gravitational attraction. Over time, these regions of higher density continued to pull in surrounding matter, eventually becoming the expansive clusters we observe today. As smaller galaxy groups merge, the process generates shock waves that heat up the surrounding gas to temperatures of millions of degrees, rendering the intra-cluster medium detectable in X-ray wavelengths. The secrets that galaxy clusters hold are manifold and crucial for our understanding of cosmology. One key mystery lies in the composition of these clusters, which are dominated by dark matter and dark energy. Observations of the gravitational effects on visible matter, light from distant galaxies, gravitational lensing, and the cosmic microwave background radiation all point towards a dark matter component that far outweighs the baryonic, ordinary matter. By studying the distribution and effects of dark matter within galaxy clusters, scientists can glean insights into its properties and role in cosmic evolution. Moreover, the hot gas that permeates these clusters, studied through X-ray astronomy, acts as a cosmic laboratory, offering clues about the chemical enrichment of the universe and the behavior of gases at extreme temperatures and pressures. Through this composite lens, galaxy clusters serve as cosmic beacons, illuminating the vast interconnected components of our universe. The cosmic microwave background, CMB radiation, is one of the most significant discoveries in cosmology, offering a snapshot of the universe when it was just 380,000 years old, a fraction of its current age of about 13.8 billion years. This faint glow of radiation, uniformly spread across the sky, is the residual heat from the Big Bang. Its discovery in 1965 by Arno Penzias and Robert Wilson provided compelling evidence for the Big Bang theory, forever transforming our understanding of the universe's origins. The CMB's importance lies not only in its existence, but in the wealth of information encoded within its subtle fluctuations in temperature. These tiny variations, on the order of 1 part in 100,000, correspond to the initial density fluctuations that eventually evolved into the large-scale structure of the universe we observe today. Galaxies, galaxy clusters, and the cosmic web. By mapping these minute differences, missions like COBE, WMAP, and Planck have provided critical insights into the universe's content, including the proportions of dark matter and dark energy, the Hubble constant, which describes the rate of expansion, and even the geometry of the cosmos. The CMB serves as a cosmic blueprint, revealing the initial conditions and subsequent evolution of the universe on grand scales. The evidence that the universe is expanding originates from several groundbreaking observations, the most prominent being Edwin Hubble's 1929 discovery of the relationship between the distance of galaxies and their redshift. Hubble observed that galaxies farther from us appear to be moving away faster, as indicated by the redshift of their light, where wavelengths are stretched, shifting towards the red end of the spectrum. This phenomenon, known as the Doppler effect, clearly suggests that the universe is not static, but expanding uniformly in all directions. The implications of an expanding universe are profound and have reshaped our conception of cosmology. One immediate consequence is the affirmation of the Big Bang theory, proposing that the universe began from an extremely hot and dense state and has been expanding ever since. This expansion also implies that the universe is finite in age, giving us a timeline for the evolution of cosmic structures from initial quantum fluctuations to the formation of stars, galaxies, and larger-scale structures. Additionally, an expanding universe leads to considerations about its ultimate fate, whether it will continue expanding forever, eventually slow down, or even contract in a big crunch. The expanding universe also encompasses the mysterious phenomena of dark energy, a form of energy that drives the accelerated expansion discovered in the late 1990s. This has led to the intriguing conclusion that about 68% of the universe's energy content is composed of dark energy, with dark matter making up about 27%, leaving a mere 5% to baryonic matter, the ordinary matter that forms stars, planets, and us. Thus, the expansion of the universe is not just a cornerstone observation, it is central to our broader quest to uncover the fundamental makeup and destiny of the cosmos. The ultimate fate of the universe is a subject of profound speculation and research, woven through with numerous leading theories that depend largely on the nature of dark energy, the universe's overall geometry, and its matter density. One of the primary scenarios, known as the Big Freeze or heat death, posits that the universe will continue to expand indefinitely. In this cold, desolate future, galaxies will drift apart, star formation will cease as raw materials are depleted, and existing stars will eventually burn out, leaving behind a dark cosmos populated by black holes, neutron stars, and cold, dead remnants. Contrastingly, the Big Crunch theory suggests a scenario in which gravitational forces could eventually halt the universe's expansion and reverse it, causing all matter to coalesce into a singularity reminiscent of the pre-Big Bang state. This theory, while intriguing, has lost traction with the discovery of accelerating expansion driven by dark energy's repulsive effects. Another fascinating theory is the Big Rip. This concept hinges on the idea that dark energy's influence might increase over time. If dark energy strengthens significantly, it could eventually tear apart galaxies, stars, planetary systems, and even atomic structures, leading to a cataclysmic end where the fabric of space-time itself is ripped asunder. Finally, there is the possibility of a cyclic universe or oscillating universe model in which the cosmos experiences an endless sequence of expansion and contraction phases, each culminating in a big crunch followed by a new Big Bang. Though compelling, this theory remains speculative and requires mechanisms to reset conditions after each cycle. These theories underscore the profound and still largely mysterious forces shaping our cosmos. Each scenario offers not just a prediction about the future, but a deeper understanding of the underlying physics governing the universe, inviting more questions and further exploration in our quest to comprehend the totality of existence. Albert Einstein's theory of relativity, encapsulating both the special theory of relativity, 1905, and the general theory of relativity, 1915, fundamentally altered our understanding of spacetime and the very fabric of the universe. Special relativity introduced the revolutionary concept that time and space are not absolute, but relative and interwoven into a single four-dimensional continuum known as spacetime. Prior to Einstein, Isaac Newton's framework of absolute time and space reigned supreme. However, Einstein's equations showed that the measurements of time and space depend on the observer's velocity relative to what is being observed. This led to mind-bending consequences such as time dilation, where a moving clock runs slower compared to a stationary one, and length contraction, where objects contract in the direction of motion as their speed approaches the speed of light. Einstein's general theory of relativity extended these ideas to include gravity, which was reconceived not as a force acting at a distance, as Newton had described, but as the warping of space-time by mass and energy. Massive objects like stars and planets create curvatures in the space-time fabric, and these curvatures dictate the motion of objects and the flow of time. This concept was spectacularly confirmed during the 1919 solar eclipse, when observations showed that light from distant stars was bent around the Sun exactly as Einstein's equations had predicted. The implications of general relativity have been profound and far-reaching. It has provided vital insights into phenomena such as black holes, whose immense gravitational fields warp spacetime to the extent that not even light can escape. It also predicted gravitational waves, ripples in spacetime caused by accelerating masses, which were directly detected a century later in 2015 by the LIGO experiment. Furthermore, general relativity is indispensable for understanding cosmic expansion and the curvature of the universe, laying the foundation for modern cosmology. Einstein's theory revolutionized not just our conceptual framework, but also our practical understanding, influencing everything from GPS technology to the deepest questions about the origin and fate of the universe. Time dilation, a key concept derived from Einstein's theory of relativity, has profound practical implications for space travel. This phenomenon occurs due to the interplay of velocity and gravitational fields, leading to scenarios where time can pass at different rates for observers in various states of motion or gravitational influence. In the context of space travel, especially at velocities approaching the speed of light, time dilation can create pronounced differences between the experiences of astronauts and those remaining on Earth. One significant implication is the potential for long-duration space missions to result in age discrepancies between astronauts and people on Earth. For example, if astronauts were to travel at speeds close to the speed of light, they could return from their journey having aged only a few years, while decades or even centuries might have passed on Earth. This effect, known as twin paradox, is not merely theoretical, but has practical ramifications for planning future interstellar missions, influencing both the logistics and psychological aspects of deep space exploration. Beyond theoretical implications, time dilation also affects current space travel technologies. For instance, the precise synchronization of clocks is critical for the operation of the Global Positioning System, GPS. Satellites in orbit experience both gravitational time dilation and velocity-related time dilation, causing their onboard atomic clocks to run at slightly different rates compared to clocks on Earth. Engineers must account for these differences to ensure accuracy in position calculations and everyday application of time dilation principles. Moreover, understanding time dilation helps in designing strategies for human exploration of distant celestial bodies. Missions to planets like Mars, which involve significant travel times and exposure to different gravitational fields, require meticulous planning for communication and coordination, factoring in the relativistic effects of both velocity and gravity. Looking ahead to potential journeys to other star systems, the relativistic effects become even more crucial, demanding advanced propulsion technologies and innovative solutions to harness the benefits of time dilation while mitigating its challenges. Time dilation is not just a fascinating theoretical insight, but a fundamental aspect of practical space travel, influencing the way we plan, execute, and conceptualize humanity's ventures into the cosmos. Gravitational waves, ripples in the fabric of space-time predicted by Einstein's general theory of relativity, have opened an unprecedented window into the cosmos. These waves are generated by some of the most violent events in the universe, such as the collision of black holes, merging neutron stars, or even the remnants of the Big Bang itself. When these massive objects accelerate, they distort space-time, sending out ripples that propagate at the speed of light. The detection of these waves provides insights into the universe's structure and the fundamental forces at play. The primary way gravitational waves deepen our understanding is through their ability to convey information about cosmic events that are otherwise difficult or impossible to study. For instance, when LIGO, Laser Interferometer Gravitational Wave Observatory, made the first direct detection of gravitational waves in 2015, it was observing the merger of two black holes. This event not only confirmed the existence of gravitational waves, but also provided the first direct evidence of black hole binaries. Such mergers emit gravitational waves that carry unique signatures, allowing scientists to deduce the masses, distances, and spins of the black holes involved. Through continuous observations, we can build a detailed catalogue of black hole collisions, contributing to our understanding of black hole formation and evolution. Moreover, gravitational waves offer insights into the extreme environments and physics at play during neutron-star mergers. These cataclysmic events can produce kilonovae, emitting elements heavy as gold and platinum, and enabling studies of nuclear physics under the most extreme conditions. The detection of gravitational waves from such events, coupled with electromagnetic observations, creates a multi-messenger approach to astrophysics, providing a comprehensive picture that can reveal the composition, structure, and behavior of neutron stars. Gravitational waves also hold potential in probing the early universe. Shortly after the Big Bang, violent processes would have generated primordial gravitational waves, providing direct clues about the universe's infancy. If detected, these primordial waves could offer empirical evidence about the inflationary period and fundamental particles, further illuminating the conditions that shaped the cosmos at its very beginning. Gravitational waves are a transformative tool in our quest to understand the universe. By allowing us to observe and analyze cosmic phenomena that are otherwise hidden or opaque, they expand our knowledge of the structure, origins, and fundamental laws governing the cosmos. This burgeoning field promises to answer some of the deepest questions in astronomy and cosmology, melding observation with theory in new and enlightening ways. Wormholes, also known as Einstein-Rosen bridges, are theoretical passages through space-time that could create shortcuts between distant regions of the universe. The concept arises from solutions to Einstein's field equations in general relativity. Imagine space-time as a two-dimensional sheet. A wormhole would be akin to folding the sheet so that two distant points touch, providing a direct path between them. The idea is tantalizing because it suggests the possibility of faster-than-light travel, circumventing the vast distances that currently limit human space exploration. However, the existence of wormholes remains speculative. While general relativity allows for such structures, they present several formidable challenges. Firstly, a traversable wormhole would require exotic matter, material with negative energy density to keep the wormhole stable and open. Exotic matter's existence is not confirmed, and creating or harnessing it, if possible, poses significant scientific and engineering hurdles. Furthermore, even if a stable wormhole could be created, the intense gravitational forces near the entrance could pose severe risks to any would-be travelers. Moreover, maintaining the stability of a wormhole against the perturbations of particles and radiation passing through it is another significant challenge. Calculations suggest that traversable wormholes, if they exist, might be extremely unstable, collapsing quickly under natural conditions. Practical considerations also include the energy requirements and technological advancements needed to locate or create such cosmic phenomena, which are far beyond our current capabilities. Despite these challenges, the study of wormholes continues to captivate and drive theoretical physics research. Concepts from quantum mechanics and the burgeoning field of quantum gravity might eventually provide new insights or even technological pathways. While wormholes currently reside in the realm of science fiction, they stimulate valuable discussions about the nature of space-time, the limits of human travel, and the fundamental laws governing our universe. In sum, while wormholes hold an intriguing potential for revolutionizing space travel, they remain a theoretical construct with numerous scientific and practical barriers to overcome. Future discoveries in physics could either bring this concept closer to reality or reveal new avenues for achieving rapid space travel, continuing to fuel humanity's dreams of exploring the cosmos. Scientists study the curvature of space-time around massive objects through a combination of precise observations and sophisticated theoretical models based on general relativity. One of the primary techniques involves observing the effects of gravitational lensing. When light from a distant star or galaxy passes near a massive object like a black hole or galaxy cluster, the massive object's gravity bends the light's path. This bending or lensing can produce multiple images of the same star, magnify the distant object, and even create arcs and rings of light. By analyzing these distortions, scientists can map the distribution and magnitude of the gravitational field, thereby inferring the curvature of spacetime in that region. Another method involves studying the orbits of stars and planets around massive objects. For instance, by tracking the paths of stars near our galaxy's central supermassive black hole, scientists can derive the black hole's mass and the curvature of spacetime around it. The most famous example is the orbit of the star S2 around the Milky Way's central black hole, Sagittarius A asterisk. The star's fast and curved trajectory provides evidence of the intense gravitational field, confirming predictions made by general relativity. More recently, the observation of the star's relativistic redshift as it approached its closest point to the black hole has provided more direct evidence of spacetime curvature. Scientists also detect the curvature of spacetime via gravitational waves, ripples created by massive accelerating objects such as merging black holes or neutron stars. Instruments like LIGO and Virgo have detected these waves, providing insights into the dynamics of spacetime around these cataclysmic events. The waveforms produced carry information about the mass and spin of the bodies involved and the nature of their collision, revealing the characteristics of spacetime under extreme conditions. Further, precise measurements of satellite orbits within our solar system, like those conducted by missions such as Gravity Probe B, have provided confirmations of frame dragging and geodetic effects, subtle shifts in the orientation of satellite gyroscopes caused by Earth's mass and rotation, again validating the predictions of general relativity. In all these cases, the interplay between observational data and theoretical models allows scientists to deeply understand the curvature of spacetime around massive objects. This not only confirms Einstein's theories, but also enhances our understanding of the universe's fundamental properties, from the behavior of black holes to the dynamics of galaxy clusters and potential insights into new physics beyond our current models. Spacetime singularities, enigmatic points where gravitational forces become infinite and the known laws of physics cease to function, are surrounded by profound mysteries that challenge our understanding of the universe. The most well-known examples of singularities are found at the centers of black holes and the very beginning of the universe, akin to the Big Bang. These regions are characterized by densities and curvatures of spacetime that are so extreme that standard concepts of space and time break down. One of the most perplexing aspects of singularities is their very existence in solutions to Einstein's equations of general relativity. These equations predict that under certain conditions, such as the collapse of a massive star, the gravitational field can become so strong that spacetime is curved infinitely. However, this prediction leads to a breakdown in determinism, where the future and past conditions of physical processes can no longer be precisely predicted. This naked singularity scenario contradicts the cosmic censorship conjecture, an idea proposed by physicist Roger Penrose, which posits that singularities should always be hidden within event horizons, beyond which they cannot influence the observable universe. The interface between general relativity and quantum mechanics is another significant area of mystery surrounding singularities. General relativity successfully describes the macroscopic world of stars, galaxies, and the cosmos at large, while quantum mechanics excels at explaining microscopic phenomena like particle interactions. Yet these two pillars of modern physics are fundamentally incompatible in situations involving extreme gravitational fields and very small scales, such as at singularities. A fully developed theory of quantum gravity, which seamlessly integrates these two frameworks, is essential to resolving the paradoxes posed by singularities. Hypotheses like string theory and loop quantum gravity aim to address these issues, but a definitive solution remains elusive. Compounding these mysteries is the information paradox, particularly significant for black hole singularities. According to classical general relativity, any information that falls into a black hole is lost to the outside universe, preserved only at the singularity. However, quantum mechanics contends that information cannot be destroyed. The reconciliation of these conflicting views challenges current theories and has led to various speculative ideas, such as the holographic principle, which suggests that information within a volume of space can be thought of as encoded on a boundary to that space. Finally, the Big Bang singularity presents its own set of questions. As we approach this initial singularity, the universe becomes incredibly hot and dense, and classical explanations break down. What existed before the Big Bang and what triggered it are profound mysteries currently beyond the reach of observational science, deeply interwoven with the quest for a unified theory. Singularities thus sit at the frontier of physics, representing both the limits of our current theories and the tantalizing promise of deeper understanding. These cosmic enigmas compel us to push the boundaries of knowledge, driving ongoing efforts to develop a more complete and unified description of the universe. Particle accelerators are sophisticated tools that provide vital insights into the fundamental nature of matter and space-time. By accelerating particles to nearly the speed of light and colliding them, these machines recreate conditions similar to those just after the Big Bang, allowing scientists to probe the fundamental forces and particles that make up the universe. One of the most famous examples is the Large Hadron Collider, LHC, operated by CERN, which accelerates protons and heavy ions to immense energies before smashing them together. These high-energy collisions produce an array of particles, some of which exist only fleetingly under ordinary conditions. By studying these particles and their interactions, scientists can test and refine the standard model of particle physics, a theory that describes the electromagnetic, weak, and strong nuclear interactions. Notably, the LHC's discovery of the Higgs boson in 2012 confirmed a crucial aspect of this model, elucidating how particles acquire mass through the Higgs mechanism. This breakthrough has ramifications for our understanding of space-time, as it offers insights into the field that permeates the universe, influencing the structure of the cosmos itself. Moreover, particle accelerator experiments explore phenomena that might offer clues about the nature of space-time at extremely small scales. For instance, examining proton-proton collisions at very high energies can potentially reveal deviations from the standard model, hinting at new physics like supersymmetry or extra dimensions. Theories that extend beyond the standard model, including string theory, suggest that space-time could have more than the familiar 4 dimensions, 3 spatial and 1 temporal. High-energy collisions might produce particles or effects that indicate the existence of these additional dimensions, thus directly affecting our understanding of the universe's underlying structure. Particle accelerators also investigate the properties of quark-gluon plasma, a state of matter thought to have existed microseconds after the Big Bang. By colliding heavy ions, physicists can recreate and study this plasma, providing valuable insights into the behavior of strong nuclear forces at extremely high temperatures and densities. Understanding these forces and states of matter helps piece together the early evolution of the universe, providing a clearer picture of how space-time and the fundamental forces have evolved. Furthermore, particle accelerators can simulate conditions that test the principles of quantum field theory and general relativity. For example, predictions about how particles should behave in strong gravitational fields can be compared against observed behaviors in high-energy collisions, offering indirect tests of these theories' mutual consistency. This is fundamental to advancing toward a theory of quantum gravity, a goal that seeks to unify general relativity and quantum mechanics. Particle accelerators serve as both microscopes and time machines, allowing us to explore the deepest layers of reality and the earliest moments of the universe. Through these experiments, scientists not only confirm existing theories, but also uncover new phenomena, stretching the boundaries of our knowledge about space-time and the myriad forces shaping the cosmos. Theoretical implications of faster-than-light FTL travel are profound and far-reaching, touching upon the very foundations of physics and our understanding of the universe. According to Einstein's special theory of relativity, as an object approaches the speed of light, its mass effectively becomes infinite, and the energy required to continue accelerating it grows without bound. This implies that FTL travel, at least in the conventional sense, is fundamentally impossible. However, speculative concepts explore the consequences and theoretical frameworks that might allow FTL travel. One of the most famous hypothetical constructs is the concept of a warp drive, inspired by Miguel Alcubierre's 1994 proposition. Alcubierre's model suggests that it might be possible to contract space-time in front of a spacecraft and expand it behind, effectively allowing the craft to surf a wave of space-time, thus traveling faster than light relative to the external space, but without locally breaking the light speed barrier. This still respects relativity because the spacecraft itself is not moving faster than light within its local space-time bubble. However, this requires exotic matter with negative energy density, something that has not been proven to exist or be feasible to utilize. Another speculative avenue involves wormholes or Einstein-Rosen bridges. If these hypothetical structures could be stabilized, they might serve as shortcuts through space-time, potentially allowing instantaneous travel between distant points. However, the stability and creation of traversable wormholes would require exotic matter and energy conditions that are currently beyond our technological and theoretical reach. Theoretical implications of such FTL mechanisms, if they could exist, are staggering. FTL travel would challenge causality, the principle that cause precedes effect. Relativity implies that FTL travel could lead to scenarios where an effect could precede its cause, potentially allowing for paradoxes such as traveling back in time. This raises complex issues about the nature of time and reality itself, requiring new physics or modified interpretations of existing theories. Moreover, the existence of FTL travel would revolutionize our understanding of distances and connectivity in the cosmos. Interstellar and even intergalactic travel could become conceivable, fundamentally altering our perspective on the universe's size and our place within it. Such capabilities would have profound implications for the search for extraterrestrial life, colonization of other planetary systems, and the ultimate future of humanity. Interestingly, some recent theoretical advancements in quantum mechanics suggest phenomena that might mimic certain features of FTL communications, such as entanglement, where particles act in correlation instantaneously over vast distances. However, these spooky actions at a distance, as Einstein called them, do not actually transmit information faster than light, and hence do not violate relativity. In sum, while the concept of FTL travel remains in the realm of theoretical speculation and science fiction, its implications are deeply intertwined with the foundations of physics. The exploration of these ideas, whether through warp drives, wormholes, or quantum phenomena, challenges us to rethink the nature of space, time, and the universe itself. Such endeavors push the boundaries of current scientific knowledge, potentially leading to revolutionary breakthroughs or profound new understandings of the cosmos. String theory, a prominent contender for a unified theory of quantum gravity, introduces a fascinating reconfiguration of the traditional concept of spacetime. At its core, string theory posits that the fundamental entities in the universe are not point-like particles, as traditionally conceived in particle physics, but rather one-dimensional strings that can oscillate in various modes. The vibrations of these strings correspond to different particles, where each vibration mode represents a distinct particle species. This shift to one-dimensional strings has profound implications for our understanding of spacetime. Firstly, string theory necessitates additional spatial dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. While the precise number can vary depending on the specific formulation of string theory, the most commonly studied versions suggest a total of 10 or even 11 dimensions. These extra dimensions are not directly observable because they are thought to be compactified or curled up at scales so small that they are effectively hidden from current experiments. The existence of additional dimensions offers potential solutions to several challenges in physics. For example, it provides a framework for unifying all fundamental forces, including gravity, within a single theoretical architecture. In traditional general relativity, gravity is despised as the curvature of 4-dimensional spacetime caused by mass and energy. In string theory, gravity is still a manifestation of spacetime geometry, but now within a higher dimensional context. This higher dimensional spacetime can manifest in various forms, leading to different physical laws in different dimensional contexts. Furthermore, string theory's higher dimensional view allows for the potential resolution of conflicts between general relativity and quantum mechanics. In the classical four-dimensional framework, singularities such as those in black holes or at the Big Bang can lead to infinities that break physical laws. String theory's extended framework, through mechanisms like string interactions and the inclusion of extra dimensions, might smooth out these singularities, potentially avoiding nonsensical infinities and providing a more coherent quantum theory of gravity. One of the most intriguing aspects of string theory's spacetime implications involves D-branes, multi-dimensional objects within the theory to which strings can attach their endpoints. These branes introduce new dynamics and lead to scenarios where our universe could be a four-dimensional slice within a higher dimensional space. This scenario, often called the brane-world hypothesis, opens the door to phenomena like gravity leaking into extra dimensions, offering potential explanations for the relative weakness of gravity compared to other fundamental forces. Moreover, string theory revives the idea of dualities, connections indicating that seemingly different physical scenarios are actually equivalent when viewed correctly. These dualities can relate different types of string theories, or even connect higher and lower dimensional theories, suggesting that space and time might be emergent properties rather than fundamental constructs. This concept further reshapes our understanding of the very fabric of reality. String theory revolutionizes the concept of spacetime by introducing extra dimensions, proposing new fundamental entities, and offering a unified framework that reconciles gravity with quantum mechanics. These innovations not only challenge traditional notions but also provide a fertile ground for addressing some of the deepest puzzles in physics, potentially leading to a more profound and comprehensive understanding of the universe. In the realm of relativity, one of the most profound and perplexing questions that remains unanswered is the reconciliation of general relativity with quantum mechanics. General relativity, formulated by Albert Einstein, beautifully describes gravity as the curvature of spacetime itself, affecting masses big and small. On the other hand, quantum mechanics governs the microscopic world with uncanny precision, explaining the behaviors of particles at the smallest scales. However, these two frameworks operate on fundamentally different principles that are not easily synthesized. The challenge of merging these two giants into a coherent theory of quantum gravity is an enigma that has puzzled physicists for decades. This quest seeks to unlock deeper layers of reality, possibly unveiling the nature of black holes, the inception of the universe, and the fabric of spacetime at the Planck scale, a mind-bogglingly tiny scale where classical and quantum effects are believed to meld together. Another tantalizing mystery in the study of relativity is the true nature of dark energy and dark matter. Observations have shown that normal matter, the stuff making up stars, planets, and all visible structures, only accounts for approximately 5% of the total energy content of the universe. An astounding 70% is attributed to dark energy, an unknown force driving the accelerated expansion of the universe, while dark matter comprises roughly 25%, influencing the formation and clustering of galaxies through its gravitational effects. Despite knowing their significant roles, scientists are still in the dark, quite literally, about the composition and mechanisms of these unseen entities. Understanding dark energy and dark matter could revolutionize our grasp of not only relativity, but also the fundamental workings of the cosmos, painting a more complete picture of the universe's past, present, and future. When it comes to the search for extraterrestrial life, scientists employ a fascinating array of methods that blend cutting-edge technology with timeless curiosity. One of the primary approaches is the study of exoplanets, planets that orbit stars beyond our own sun. Using instruments like the Kepler Space Telescope and its successor, the Transiting Exoplanet Survey Satellite, TESS, scientists identify potential exoplanets by observing the dimming of a star's light as a planet transits or passes in front of it. Once identified, these exoplanets are analyzed for their habitability potential. This involves calculating the planet's distance from its star, which determines whether it lies within the habitable zone, where conditions might be right for liquid water, a key ingredient for life as we know it. Additionally, powerful observatories like the upcoming James Webb Space Telescope will probe the atmospheres of these distant worlds, searching for biosignatures, which are chemical markers like oxygen, methane, or water vapor that could suggest the presence of life. Another intriguing method involves the study of extremophiles here on Earth. Extremophiles are organisms that thrive in extreme conditions, such as the intense heat of hydrothermal vents at the ocean floor, the acidic environments of sulfuric hot springs, and the frigid radiation-bathed terrains of Antarctica. By understanding how life can survive in such harsh conditions, scientists gain insights into the potential for life to exist in similar environments elsewhere in the solar system and beyond. In our own solar system, missions such as the Mars rovers, including the latest Perseverance rover, are equipped with sophisticated instruments designed to detect signs of past or present life on the red planet. Similarly, missions to icy moons like Europa, which harbors a subsurface ocean beneath its frozen crust, aim to uncover biochemical evidence of life. Additionally, radio telescopes involved in the search for extraterrestrial intelligence, SETI, listen for potential signals from advanced extraterrestrial civilizations. Each method, whether grounded in the observation of distant exoplanets or the exploration of nearby moons and planets, represents a step forward in humanity's enduring quest to answer one of our most profound questions: are we alone in the universe? The study of extremophiles on Earth has profoundly informed and expanded the horizons of our search for life on other planets. Extremophiles are organisms that thrive under conditions previously thought to be uninhabitable: extremely high or low temperatures, intense pressures, high acidity or alkalinity, and high levels of radiation. These remarkable adaptations challenge the traditional parameters of what constitutes a life-supporting environment and suggest that life could potentially exist in a much wider array of conditions than previously believed. For instance, the discovery of thermophiles which flourish in the boiling waters of hydrothermal vents deep in the ocean has led scientists to consider the possibility of life on celestial bodies with similar environments. Take, for example, the icy moons of Jupiter and Saturn, Europa and Enceladus, which are believed to harbor subsurface oceans kept warm by the gravitational interactions with their parent planets, creating conditions akin to these deep-sea vents. Similarly, acidophiles and alkalophiles, which live in highly acidic or basic environments, have inspired the search for life in the sulfuric acid clouds of Venus or the alkaline hydrothermal vents on Mars. Moreover, the study of extremophiles such as radio-resistant microbes, which can survive extreme levels of radiation, broadens the potential habitability zones within our own solar system and beyond. Mars, with its thin atmosphere and high radiation levels at the surface, might still harbor microbial life underground, where it could be shielded from the harshest conditions. Analogues like Antarctica's dry valleys, where psychrophiles, cold-loving organisms, thrive, also provide a terrestrial model for potential life forms that might exist on the frozen plains of moons like Europa or Enceladus, or even in the polar regions of Mars. Extremophiles demonstrate the incredible resilience of life and encourage scientists to think more broadly and creatively about where life might exist. The discovery that life can thrive in Earth's most extreme environments extends the range of conditions considered habitable, guiding astrobiologists to seek signs of life in places once deemed improbable. This pioneering perspective underscores our expanding understanding of life's versatility and fuels the optimism that we might someday find life beyond Earth. One of the most compelling pieces of evidence for possible extraterrestrial life is the discovery of exoplanets within their star's habitable zone, or the Goldilocks zone, where conditions could be just right for liquid water to exist on the planet's surface. Since the launch of the Kepler Space Telescope, scientists have identified thousands of exoplanets, with several located in this habitable zone. These planets, like Kepler 452b and Proxima Centauri b, offer intriguing possibilities due to their Earth-like conditions, which theoretically could support life. The detection of organic molecules in space adds another layer to the evidence. Organic molecules, such as amino acids, are the building blocks of life, and their presence in meteorites, comets, and the interstellar medium suggests that the ingredients for life might be widespread throughout the galaxy. Notably, the discovery of complex organic compounds on Saturn's moon Titan and within the plumes of water vapor ejected from the ocean beneath the icy crust of Enceladus hints at chemical processes that could potentially support life. Closer to home, Mars has provided tantalizing hints of past and possible present life. The Curiosity rover detected methane spikes in the Martian atmosphere, which on Earth is largely produced by biological activity. While methane can also be generated by geological processes, its seasonal variation on Mars leads scientists to consider the fascinating possibility that microbial life could be producing it. Furthermore, sedimentary rocks analyzed by rovers have revealed ancient riverbeds and lake deposits, suggesting that Mars once had liquid water running on its surface for extended periods, a crucial ingredient for life. Another persuasive piece of evidence comes from the study of extremophiles on Earth, organisms that can survive in the most inhospitable environments. These include microbes found in the acidic hot springs of Yellowstone, the freezing ice of Antarctica, and the crushing depths of the Mariana Trench. The existence of such resilient life forms broadens our understanding of the possible diversity of life and signifies that life could potentially survive in the extreme conditions found on other planets and moons. These clues collectively generate strong enthusiasm and ongoing exploration in the quest to find extraterrestrial life. While none of this evidence confirms the existence of life beyond Earth, each discovery builds a case that life as we know it, or as we might not yet know it, could very well exist somewhere else in the cosmos. The evolution of life in environments vastly different from Earth challenges our imagination and scientific understanding, but the principles of biology and evolution provide a framework to hypothesize how such life forms might develop. On a high-gravity planet, for instance, evolutionary pressures could produce organisms with strong, robust structures to withstand the increased force. These beings might have much denser muscles, more powerful limbs, and compact, squat physiques to support their body structure. The increased gravity would also likely influence the development of cardiovascular systems designed to efficiently combat the force pulling blood downwards. In an environment with high radiation levels, such as a planet orbiting a star that emits intense UV or X-rays, life forms might evolve extraordinary mechanisms for DNA repair and radiation resistance. For example, microbial life equivalents could possess highly efficient enzyme systems that rapidly repair damaged genetic material, while multicellular organisms might develop protective layers of pigment or exoskeletons to shield their internal organs. These adaptations would mirror some of the extremophiles on Earth, like the radio-resistant bacteria Deinococcus radiodurans, which can survive incredibly high doses of radiation due to its impressive DNA repair capabilities. In chemical environments vastly different from Earth's, such as the methane lakes of Titan, life could evolve utilizing entirely different biochemistries. Instead of water, these organisms may use liquid methane or ethane as a solvent for their biological processes, leading to biochemistries that are profoundly different from our carbon-water-based life. Their cellular structures might be composed of membranes that withstand the extreme cold, and their metabolic processes would need to be highly efficient to generate energy under such conditions. Scientists speculate that silicon, rather than carbon, could be the backbone of such biochemistry, providing a theoretical basis for silicon-based life that might function in these exotic environments. Photosynthesis, a fundamental process for many life forms on Earth, might also undergo radical changes under different star types. On a dim, red dwarf star-illuminated planet, photosynthetic organisms might evolve pigments that can absorb infrared light, which is more abundant from such stars. Conversely, on planets orbiting hotter stars that emit more UV radiation, organisms might develop protective mechanisms and pigments that effectively capture and utilize this more energetic light while protecting against its damaging effects. These hypothetical scenarios demonstrate the incredible adaptability of life, governed by the principles of evolution by natural selection. While the exact forms and functions of extraterrestrial life remain speculative, studying extremophiles on Earth gives us invaluable insights into how life might thrive under conditions that are vastly different from our own. This expands our understanding of life's potential diversity and adaptability, fueling our exploration and search for life beyond our home planet. The discovery of microbial life on Mars would be a scientific milestone with far-reaching implications, reshaping our understanding of life in the universe and our place within it. First and foremost, it would provide concrete evidence that life is not unique to Earth, suggesting that the conditions necessary for life might be more common than we currently assume. This would significantly boost the probability of finding life elsewhere in the cosmos, particularly on the many exoplanets identified within their star system's habitable zones. One of the major scientific implications would involve the study of Mars' geology and climate history. Microbial life would likely have adapted to Mars' present conditions, but understanding its origins could reveal vital information about Mars's past environments. If life originated independently on Mars, it would suggest that life can emerge under a broader range of conditions than those found on early Earth. Alternatively, if Martian microbes share characteristics with Earth life, it might support theories of panspermia, which propose that life can be distributed across planets via meteoroids, comets, or other celestial bodies. The discovery could spur significant advancements in astrobiology, particularly in developing methods and technologies for detecting life in extreme environments. Such findings would drive missions to other celestial bodies in our own solar system, like Europa, Enceladus, and Titan, which are also considered potential habitats for life. It could also accelerate funding and research into more sophisticated space missions designed to explore these distant moons and planets with the precision needed to uncover microbial communities. Ethically and philosophically, discovering Martian microbes would challenge humanity's self-perception. It would prompt profound questions about the uniqueness of human life and the broader potential for intelligent civilizations in the universe. The discovery might also influence discussions about the moral considerations of colonizing Mars or other celestial bodies. Protecting and preserving extraterrestrial ecosystems could become a priority, transforming the legal and ethical frameworks governing space exploration. On a practical level, the discovery would have significant implications for planetary protection protocols. Current measures aim to prevent contamination of both Earth and other celestial bodies. If life is found on Mars, ensuring that Earth's microbes do not interfere with Martian ecosystems would become even more critical, and vice versa. This could lead to more stringent sterilization processes for spacecraft and advanced quarantine procedures for samples returned to Earth. The discovery of microbial life on Mars would be a watershed moment in science, influencing our understanding of biology, driving technological and exploratory advancements, and prompting deep ethical and philosophical reflections. It would mark a transformative step in humanity's quest to comprehend the full scope and diversity of life in the universe. SETI researchers who are dedicated to the search for extraterrestrial intelligence utilize a range of sophisticated techniques and technologies to listen for signals from intelligent civilizations beyond Earth. At the core of their efforts are powerful radio telescopes, which scan the sky in search of radio waves that might be indicative of artificial rather than natural origins. These telescopes are capable of detecting a broad spectrum of frequencies, yet SETI scientists often focus on a narrow band around 1,420 MHz, known as the water hole. This frequency is significant because it is naturally emitted by neutral hydrogen, the most abundant element in the universe, and might be a logical choice for an intelligent civilization attempting interstellar communication. The quest involves more than just random listening. It requires an organized approach to data collection and analysis. Advanced algorithms and software are employed to sift through the immense volumes of data collected, filtering out Earth-originating noise and other celestial sources of radio waves. The aim is to identify narrow bandwidth signals that stand out against the random hiss of the cosmic background, because such signals are generally understood to be produced by technological sources. Projects like SETI at home have even enlisted the help of millions of volunteers around the globe to use their personal computers' processing power to analyze chunks of data, democratizing the search and exponentially increasing the computational capacity available to the researchers. Optical SETI is another promising avenue, involving the use of optical telescopes searching for brief but powerful laser pulses that might be sent by distant civilizations. These pulses, detectable over vast interstellar distances, would be a clear indicator of intelligent technology. State-of-the-art photodetectors attached to telescopes scan the sky for such fleeting bursts of light, which are distinct from the continuous luminescence of stars. A further layer of sophistication is added by the targeted searches, which focus on specific star systems identified as having potentially habitable exoplanets. As our understanding of exoplanets has improved, thanks to missions like Kepler and TESS, SETI researchers can now direct their instruments toward the most promising candidates, thus increasing the likelihood of detecting something noteworthy. Additionally, SETI research doesn't operate in isolation but collaborates with other astronomical surveys and observatories around the world. This coordination enhances their ability to verify potential signals quickly and rule out terrestrial interference, thereby ensuring that any candidate signal is scrutinized from multiple perspectives. The implications of detecting a signal from an intelligent extraterrestrial civilization would be monumental, forever altering our understanding of humanity's place in the cosmos. As such, SETI researchers meticulously document their findings and engage in robust peer review processes to validate any potential discoveries. Until that momentous day comes, the ongoing efforts represent humanity's enduring curiosity and quest to answer one of our most profound questions. Are we alone in the universe? The WOW signal, detected in 1977, remains one of the most tantalizing and enduring mysteries in the search for extraterrestrial intelligence. On August 15th of that year, Jerry R. Amon, a volunteer astronomer working on the Ohio State University's Big Ear radio telescope, observed an anomalous, 22 times stronger than typical cosmic background, narrow bandwidth radio signal. The signal, which lasted 72 seconds, was so striking that Amon circled it on the computer printout and wrote, "Wow," in the margin, giving the signal its now famous name. One of the key mysteries surrounding the WOW signal is its origin. The signal appeared to emanate from a region within the constellation Sagittarius, close to the Sagittarius star group, about 120 light-years away. However, despite numerous follow-up attempts to locate the signal, neither Amon nor subsequent astronomers have been able to reproduce or detect it again. This singularity has led to extensive speculation about whether the WOW signal was a genuine extraterrestrial transmission or the product of some rare and poorly understood natural phenomenon. The signal's specific characteristics add to the intrigue. The WOW signal exhibited a narrow bandwidth, only about 10 kHz, which is consistent with an artificial origin. Cosmic sources typically produce a broad range of frequencies, making such narrow-band signals highly unusual and consistent with the kind of focused broadcasts we might expect from an intelligent civilization attempting to communicate across vast interstellar distances. Moreover, its frequency, at approximately 1,420 MHz, coincides with the emission line of neutral hydrogen, a universal marker that scientists speculate would be an ideal frequency for interstellar communication. Several hypotheses have been proposed to explain the WOW signal, ranging from interstellar scintillation to terrestrial interference. However, none have been definitively proven. The possibility that it might have been a deliberate broadcast from an alien civilization continues to captivate imaginations, although the lack of repeat detection makes it difficult to draw firm conclusions. Some skeptics suggest the signal may have been an Earth-based transmission reflected off a piece of space debris, but this remains speculative with no concrete evidence. Adding to the layers of mystery is the fact that the Big Ear telescope was designed to survey the sky in two orthogonal directions, but only one channel detected the signal while the other did not. If the signal had a terrestrial or near-Earth origin, it would likely have been detected in both directions. The duration and shape of the signal also do not match known satellite transmissions, further complicating efforts to explain it away with conventional sources. The WOW signal's elusiveness underscores the challenges inherent in the search for extraterrestrial intelligence. It serves as a reminder both of the vastness of the cosmos and the limitations of our detection capabilities. Decades later, the mystery of the WOW signal continues to inspire both professional astronomers and amateur stargazers to keep watching the skies, hoping that perhaps one day a similar signal might offer more conclusive evidence of intelligent life beyond Earth. Until then, the WOW signal remains one of the most compelling enigmas in the annals of astronomy. Life's potential existence on the moons of Jupiter and Saturn has become a focal point of astrobiological research, primarily due to the unique environments these distant worlds offer. Europa, one of Jupiter's moons, and Enceladus, orbiting Saturn, are particularly compelling due to their subsurface oceans, which are kept in a liquid state by tidal heating, a result of gravitational interactions with their parent planets and neighboring moons. Europa, with its smooth, icy surface crisscrossed by dark streaks and ridges, is believed to possess a vast ocean beneath its frozen crust. The evidence comes from observations by the Galileo spacecraft, which detected a magnetic field indicative of a salty, conductive liquid beneath the ice. This subsurface ocean might be in contact with a rocky mantle, potentially allowing for the chemical interactions necessary to support microbial life. If hydrothermal vents exist on Europa's seafloor, similar to those found in Earth's oceans, they could provide the energy and nutrients needed for life. These deep-sea vents on Earth host ecosystems teeming with life, independent of sunlight, relying instead on chemosynthesis to convert chemicals into energy. Enceladus, although smaller, presents an equally fascinating case. The Cassini spacecraft made remarkable discoveries during its flybys, capturing images of geysers erupting from the Moon's south polar region. These plumes are composed of water vapor, molecular hydrogen, and organic compounds, suggesting a subterranean ocean beneath the icy shell. The presence of molecular hydrogen, detected during Cassini's investigations, indicates hydrothermal activity on the ocean floor, where water rock interactions produce hydrogen. This environment could provide a source of chemical energy for life, similar to the ecosystems found near Earth's hydrothermal vents. Titan, another moon of Saturn, offers a different yet intriguing environment for potential life. Unlike Europa and Enceladus, Titan has a thick nitrogen-rich atmosphere and liquid hydrocarbon lakes on its surface, primarily composed of methane and ethane. While this is vastly different from the water-based life we know, it is conceivable that life could evolve using these hydrocarbons as solvents. Scientists theorize that Titan's exotic chemistry might allow for the formation of complex organic molecules and possibly prebiotic chemistry, which could serve as precursors to life. Ganymede and Callisto, two of Jupiter's other large moons, also exhibit signs suggesting subsurface oceans. While less studied, the potential for liquid water underneath thick ice layers adds them to the list of intriguing candidates. The idea that life could survive in these alien environments is supported by the discovery of extremophiles on Earth, organisms that thrive in extreme conditions, from boiling acidic springs to deep subterranean rocks, demonstrating life's remarkable adaptability. Exploring these moons to confirm the existence of life involves several technological challenges and future missions. Instruments designed to analyze the composition of surface ice, study plumes, and potentially drill through ice layers to reach underlying oceans are in various stages of development. NASA's upcoming Europa Clipper mission aims to conduct detailed reconnaissance of Europa's ice shell and subsurface ocean, while the European Space Agency's JUICE mission will study Jupiter's icy moons, including Ganymede. In all, the moons of Jupiter and Saturn represent some of the most promising locations in our solar system to find extraterrestrial life. The presence of subsurface oceans, organic molecules, and energy sources in these distant worlds offers compelling conditions that might support living organisms. Uncovering such life would revolutionize our understanding of biology, biochemistry, and the potential prevalence of life in the universe, offering profound implications for our place in the cosmos. Confirming the existence of extraterrestrial life is a monumental scientific task fraught with numerous challenges, spanning technological, methodological, and philosophical domains. One of the primary challenges is the vast distance and scale of space. Even within our own solar system, destinations like Mars, Europa, and Enceladus require significant travel time and resources to reach. Interstellar distances magnify this challenge exponentially. The nearest star system, Alpha Centauri, is over 4 light-years away, making direct exploration with current technology impractical. Another significant hurdle is the detection and identification of indirect evidence of life or biosignatures. These can take many forms: chemical markers, unusual atmospheric compositions, or even complex organic molecules. For example, the presence of methane spikes on Mars detected by the Curiosity rover remains intriguing but inconclusive. As such, methane could be produced by geological processes rather than biological ones. Similarly, observing oxygen, methane, or water vapor in exoplanet atmospheres with telescopes like the upcoming James Webb Space Telescope could hint at life, but distinguishing between biological and abiotic sources is challenging. The environment itself poses formidable obstacles. Harsh conditions such as extreme radiation, low temperatures, or high pressures necessitate specialized equipment for exploration and sample collection. Rovers and landers designed to explore these environments must be robust and capable of conducting sophisticated analyses remotely with minimal error. Technological limitations also extend to our current inability to drill deep through ice shelves to access subsurface oceans on moons like Europa and Enceladus, where life could potentially exist. Contamination control is another critical issue. Ensuring that any potential life detected on other planets or moons is genuinely extraterrestrial rather than a stowaway from Earth requires rigorous sterilization of spacecraft and instruments. Conversely, bringing extraterrestrial samples back to Earth must be done with extreme caution to avoid contaminating our biosphere with potentially unknown and hazardous microorganisms. Scientific consensus and reproducibility further complicate the confirmation process. Any claim of discovering extraterrestrial life must undergo thorough scrutiny, peer review, and independent verification. The implications of such a discovery are so profound that the scientific community mandates exceptionally high standards for evidence. This means that even if a potential biosignature is detected, it must be observed consistently and corroborated through multiple lines of evidence and by different teams of researchers. Detection of intelligent extraterrestrial life presents its own set of challenges. Projects like SETI involve listening for radio signals from intelligent civilizations, but deciphering these signals, distinguishing them from human-made interference, and confirming their extraterrestrial origin is a complex and daunting task. The famous WOW signal detected in 1977 is a prime example of an intriguing yet unrepeatable anomaly, leading to ongoing debates and further investigations without definitive conclusions. Finally, there are philosophical and definitional challenges. What constitutes life? Traditional definitions based on Earth biology might not apply to life forms with fundamentally different biochemistries. The concept of life as we don't yet know it forces scientists to expand their criteria and approaches, ensuring they don't overlook non-Earth-like forms of life simply because they don't fit preconceived notions. Confirming extraterrestrial life requires overcoming immense distances, developing advanced technology, managing contamination risks, ensuring reproducible and robust scientific evidence, deciphering potential intelligent signals, and broadening our understanding of what life could be. These challenges are daunting but also drive innovative solutions and interdisciplinary collaborations, pushing the boundaries of science and our understanding of the universe. The discovery of extraterrestrial life would revolutionize our understanding of life on Earth in several profound ways, impacting fields as diverse as biology, philosophy, astronomy, and even theology. From a biological perspective, finding extraterrestrial life would provide invaluable insights into the diversity and adaptability of life. It would expand our understanding beyond the Earth-centric view of biochemistry and provide a comparative framework within which to study the principles of life. For instance, if extraterrestrial life were discovered to utilize biochemistries different from carbon-based life, perhaps silicon-based or based on an entirely unforeseen molecule, it would prompt a re-evaluation of the fundamental prerequisites for life and might reveal new biochemical processes previously considered impossible. This discovery would invigorate evolutionary biology by offering a new context for studying how life evolves under different environmental conditions. On Earth, evolution is driven by various pressures such as climate, geography, and chemical availability. Discovering life that evolved under different conditions, say in the high radiation environment of an exoplanet orbiting a red dwarf star or in the frigid methane lakes of Titan, would offer new evolutionary pathways and mechanisms, broadening the scope of evolutionary theory. Philosophically, the confirmation of extraterrestrial life would challenge long-held views about humanity's place in the universe. The Copernican principle, which posits that Earth is not the center of the universe, would gain even more significance, suggesting that life is a ubiquitous phenomenon rather than an earthbound anomaly. This paradigm shift could influence philosophical discussions about the uniqueness of human life, our ethical responsibilities toward other life forms, and our role in a broader, perhaps teeming cosmic ecosystem. Theologically, the discovery might prompt reinterpretations of religious doctrines and texts, particularly those concerning the uniqueness of human life and the concept of creation. Different religions might integrate these new discoveries into their worldviews in various ways, potentially leading to a richer, more nuanced understanding of spirituality that encompasses a universe filled with life. In terms of scientific methodology, discovering extraterrestrial life would underscore the power and importance of interdisciplinary research. combining astronomy, chemistry, biology, and environmental science, among other fields. It would necessitate the development of new scientific instruments and methods for detecting, analyzing, and understanding life forms with potentially unfamiliar anatomies and biochemistries. This technological and methodological innovation could have spillover benefits for other scientific fields and disciplines. From a societal and cultural perspective, the discovery could foster a new sense of unity and purpose. Humanity might come to see itself as part of a larger cosmic family, prompting global cooperation in scientific, environmental, and exploratory endeavors. It might also incite scientific curiosity and inspiration, similar to the excitement and wonder generated by the Apollo moon landings, but on an even grander scale. Economically, such a discovery could drive investments in space exploration, biotechnology, and related industries, leading to technological advancements and new market opportunities. The quest to explore, understand, and perhaps even communicate with extraterrestrial life could become a major driver of innovation and economic growth. The discovery of extraterrestrial life would have transformative implications for our understanding of life on Earth, reshaping scientific paradigms, philosophical perspectives, theological beliefs, and societal values. It would confirm that life is a fundamental cosmic phenomenon, prompting humanity to rethink its place in the universe and its relationship with other forms of life, potentially leading to a more united and enlightened global community. As humanity advances, what new discoveries do you think could happen? Could we ever find evidence of extraterrestrial life in the universe, or will we be the only ones? Let us know your thoughts in the comments below. Thanks for watching.